We can start?
Just a second. Yeah, I think so.
Good afternoon, everybody. It's a pleasure to be here in this conference, the 17th IEEE Latin America Robotics Symposium. Now we start with the section Aero Vehicles 1. Just to remember, the authors can present themselves or by video option. And we start this section with the paper entitled A Novel Concept for Hybrid Unmanned Aerial Underwater Vehicles Focused on Aquatic Performance. The presenter is Pedro Pinheiro. Pedro, do you want to present or use a video?
To use the video.
Okay.
Just a second.
Hello everyone, my name is Pedro Pinheiro, I'm a graduate student
at Universidade Federal do Rio Grande, and I'll be presenting a work titled A Novel Concept for Hybrid Unmanned.
Can you hear the video?
Yes, we can.
Okay, I just started.
Aerial underwater vehicles focused on aquatic performance. This work was done by Alexandre Horn from Instituto Federal de Educação, Ciência e Tecnologia Sul-Rio Grandense, myself, Ricardo Grando from Universidade Federal do Rio Grande, César da Silva from Universidade Estadual de Campinas, Professor Armando Neto from Universidade Federal de Minas Gerais, and Professor Paulo Drills from Universidade Federal do Rio Grande. I'll start now with a brief introduction. Hybrid unmanned aerial underwater vehicles are systems that can navigate in air and underwater and do not require change in geometry to perform transition. This means that they combine the characteristics of unmanned aerial vehicles and unmanned underwater vehicles. And they have a great challenge, which is to deal with two really different specific masses for each media. Our motivation here is that many applications require transit in both media for full perception, such as search and rescue, environmental research, and inspection of partially submerged structures. So these vehicles are really needed, but the current state of the art penalizes motion efficiency in favor of simplicity and ease of control. So our problem in this work was to design a new concept of a hybrid vehicle that focuses on both aerial and underwater performance. Now I'll show you some of the related works. On the left, we have the first concept of modern AUAUV, which was proposed by Drills et al. From 2014. On the right, we have the first transmedia focused concept, which was proposed by Ma et al. From 2018. And both of them have 4 aerial propellers and 4 underwater propellers. The second one has also 2 frames. Now I'll show you 2 of the most recent proof of concept prototypes. On the left, we have the Navigator, which has 8 coaxial aerial propellers. And the second one on the right is the Lungcopter, which has 4 aerial propellers plus a ballast, which is a system that fills with water in order to control the buoyancy. Both of them need to turn 9 degrees to move forward, which is not a good thing because you have a larger drag force on the vehicle. And the last one is a 4 aerial propeller with fixed wings and a bladder for underwater glider motion. It is a concept that combines UAV with underwater glider and is really different from the others. So you may notice that none of these concepts has forward-facing propellers. And this is a great issue because they have high drag force due to large area normal to the vehicle motion. Now I'll show you our methodology. This is the high drone system design. Is our proposed concept. It has one set of coaxial air underwater propellers and a second set which is perpendicular aerial underwater propellers. Since it has forward-facing propellers, it has a lower drag, but it has no roll angle control underwater, relying only on static stability and moving like an Ackermann vehicle. It also has a positive buoyancy. This is our dynamic model. It has some specificities, which I'll show you now. Some of them is the mass plus added mass term, the translational drag coefficient term, the net weight, which is due to buoyancy, the switched actuator forces term, which is due to 2 separate systems, one for the air, one for the water, the inertia tensor plus added inertia term, the rotational drag coefficient term, the rotational static stability term, and the switched actuator moments term. Now, this is our z-axis control. You may notice that we only have 2 actuators for the z-axis control underwater. This is our attitude control, where you may notice that we have no roll angle control. This is the aerial y and x-axis control, which is done by changing the roll and pitch angle. And this is the underwater nonlinear control law. Now for our experiments, this is our used simulation used parameters. You may notice that our vehicle has a positive buoyancy here, and it also has a 2 centimeters between the center of mass and the center of buoyancy, which is done by to improve our static stability. These are the propeller parameters. You may notice that we have 2 sets of parameters for aerial propellers, and this is because some of the concepts used in a comparison that I'll show you later, they use aerial propellers underwater. I'll show you first our waypoint navigation simulation. Our vehicle motion is like a classic UAV on the air, and underwater is able to navigate with the 2 forward-facing propellers. It gives a higher speed, lower drag, and you may also notice that we have the switched actuator on the bottom right corner. Okay, now I'll show you our comparative analysis. The vehicles had to track this reference trajectory, and you may notice that Hydrone was performed really well in this, while the other three concepts were pretty similar. Only Al-Zubi et al. From 2018 had some trouble with the z-axis, and this is due to the ballast system, which has to fill with water and it takes time. And for the comparative analysis, we had this energy equation, and you may notice that our vehicle was able, in the same time, as the others, it was able to move in for 51 meters, and it also has a great energy distance ratio, which is really good comparing with the others. And this is mainly due to the aquatic specialized propellers and the lower drag forces. So our conclusions and future work, our proposed concept, Hydrone, maintains aerial quadrilateral performance. It has better hydrodynamics than the current state of the art. So it has a higher underwater energy efficiency. And it relies on static stability and non-holonomic kinematics. For our future work, we'd like to build and evaluate a prototype in real-world applications. We are currently working a lot on this. And we will also design a robuster control strategy to guarantee the stability under disturbances. If any of you has some questions, you may ask me right now on Zoom or email me. Thank you very much. I would like also to thanks CAPES and CNPq, and also PRH from ANP. Thank you very much.
Thank you very much, Pedro. Congratulations. I found your work extremely interesting. And congratulations for the video. It was really well done. So this kind of systems, it's increasing the interest by researchers and industry. So I really found this very interesting. You said in future works that you have you're going to build a prototype. So, but by curiosity, do you have already undergoing a physical prototype?
Yes. The issue here is the high underwater pressure. So we have to protect the electronics. So this is our main challenge, because you have to do it and keep the lightweight. So and because of the pandemic, we are working from home. I also would like to thank the team, because they are doing a great job working from home. But yeah, this is currently the main challenge, and we hope to have a working prototype by the end of the year, maybe the beginning of 2021.
Okay, and another curiosity, when you are performing this underwater navigation, are you considering some dynamics of the water or not?
Yes, actually, in this simulation, we mainly focus on the water drag.
Okay.
The drag due to the water resistance, right? In the future work, we intend to add some disturbances such as water flow, wind, and a
Yeah,
lot of things
wind,
that happen in the real world,
waves, more constraints to your model.
Yeah, because working with UAVs is very challenging because
Yeah, for sure.
it's not cost effective because you have sometimes you have only one prototype and you have to take care. So we are working a lot with simulation right now to improve the best we can.
Yeah, another issue I think that you said before is the splash zone when the drone needs to go to the water. So I think this is a main challenge too. So in this work, you are not analyzing this, right?
Actually, in the current state of the art, no one is working on the media transition because it's really hard. We are also working on it. We intend to add to the simulation as well. But the media transition requires a very complex maneuver. So we intend to simulate it as well to develop the best strategy we can.
Okay, congratulations again.
Thank you.
I don't know if you have some questions on YouTube.
There's no questions from YouTube, but I would like to ask something. I'm Professor Julio. I work with Luis and many other professors, and we also have some experience on drones. And we are working on different directions right now. But still, I am very curious about your project. I was mainly concerned about what are the applications, because your research is founded by AMP. So there should be some interest, but since the prototype, or at least in your results, is not going very deep, I was just curious about the real applications that you are thinking of.
Yes. Thank you. So as I said before, the main concern is to keep the lightweight to have a energy efficient flight. So currently, this is also in the whole state of the art. These vehicles, they don't go too deep, so they are very good for partially submerged structures such as oil platforms, for example. But you cannot go too deep, so you have to keep maybe 5 meters, 10 meters underwater, and that's a lot for this kind of vehicle right now.
So thank you, Pedro. Congratulations. So moving on to the paper, GPS spoofing detection, detecting GPS fraud in unmanned aerial vehicles. Unfortunately, the presenter has some health issues, so the presentation will be by video.
Just starting right now.
Hello, I am Isadora. I am a master's degree at the University of São Paulo. I will present the work entitled GPS Spoofing Detecting in GPS Fraud in Unmanned Aerial Vehicles. This research is funded by the fund Agence CAPS. This will be the presentation schedule. This work involves the use of unmanned aerial vehicles, so the
Julio, is it okay in there? You got a problem?
Can you hear me? Can you hear me?
Yes.
Yes.
I don't know why the video is not. I will just try to refresh, maybe.
Don't you have the video in your computer?
No, did not download it.
Oh.
Yeah, next time. I think so.
Hello, I am.
Now it's okay.
Okay, go ahead.
Isadora. I am a master's degree at the University of São Paulo. I will present the work entitled GPS Spoofing Detecting in GPS Fraud in Unmanned Aerial Vehicles. This research is funded by the fund Agence CAPS. This will be the presentation schedule. This work involves the use of unmanned aerial vehicles, so the starting point of this presentation begins with the definition of the concept. A drone, UAV or ARP, is a machine capable of operating without a pilot on board who directly and actively controls the device. Technology progress in electronic and avionics systems, especially of miniaturization and cost reduction, has increased the academic and economic interest to market and study these aircraft. Due to their numerous applications, UAV are likely to be part of our daily lives, but not without challenges. One is how to insert UAVs into shared airspace. They must be supervised that their flight's path and communication do not affect current air traffic. UAV must continually adapt to mission and detect unexpected internal problems or external dangers, so they need to be autonomous. However, on the most critical parts in the safety and security challenge, they represent a serious threat to drone and can cause injuries to humans, the environment, and also loss of wide valuable assets. The vulnerability of GPS systems has been a major concern of military and civilian aviation. Its most recurrently failure has a low level of complexity of exploration and leads to compromised missions through the possibility of the vehicle death and even destruction after a fall. Spoofing attack is a situation in which a person or program successfully identified as another by falsifying data to gain an illegitimate advantage. Based on what was previously mentioned, this work proposed to detect GPS spoofing in unmanned aerial vehicles through two metrics: one for safety in physical security, and another for security computational security. The hamster, the mobility and security based and communication architecture hamster, it is within the safety and security metrics were implemented. The hamster is divided in three categories: flying hamster, swimming hamster, and running hamster. Hamster integrates four platforms: NCI, NP, Sphere, and Nibble. Sphere platform is focused on architecture, security, and safety issues. This paper will cooperate with Sphere platform. Sphere platform is focused on architecture, security, and safety issues. Within this sphere, we have three modules that work metrics: CSU, CPMU, and CMU. CSU is responsible for authentication and confidentiality. CPMU is responsible for managing the registration, discovery, and the CMU is responsible for monitoring the integrity of the modules. Inside the CSU will be security metric implemented in this work, and inside the CMU, the safety metric. The security metric is hover sign, and the safety metric is NCI. NCI measures the critical level of a node in the work, that is helping to determine priorities for node in a network, provides valuable information to the system that can influence the task decision making. The NCI safety is a modular. NCI can be found the averaging the integrity and priority of the module. After a data is collected for the CSU, the haversine form is applied. The haversine form is an equation used in navigation to provide distance between points in a sphere. From the collection, it's a geographical coordinates. It used to calculate the distance of the largest circle between 2 points. That is the shortest distance on the Earth surface given distance between 2 points. Ignoring any hills, they fly. Finally, after applying haversine, the time collected calculates the average speed of the drone along with the distance. From this, we have instance information, hour and minute, distance and speed, whose metrics are used in this work check the GPS security in UAV. The metrics were explored in 3 different scenarios. In GPS spoofing, with the IDEA Mobile Comforter app, and also implementation and validation with a held drone architecture. The hamster, which was mentioned early, starting then with case study. That's where the stages of development, choice of mission is an organ transplant scenario. This study consists in 2 scenarios, a normal operation and aircraft files, and requires a by decision human operator. The aircraft is 3DR solo. The reason for choosing the aircraft is that it has an autopilot. Stipulation of values. The data load used for the analysis of security metric was collected with the 3DR solo in São Carlos, São Paulo, Brazil. In the step, the values were assigned to their respective formulas for security and safety. In the table, we have a test case for a normal transplant operation. Latitude and longitude correspond to the start point at 13:31 p.m., the median distance 2 points, and the arrival point. We have NCE data table, safety metric. The values were assigned as follows. The EMU and the autopilot manipulate data related to the solo position, so their priority to set 0.5 is if solo is forced to HAL. It's necessary to establish Wi-Fi communication to locate and retrieve the UAV, which justifies its value 0. as priority. Is there a sudden change in location and the drone travel at a distance in a period and shown in the table? Then GPS spoofing alert is issued the station. The decision-making model is invoked. If case of GPS failure in the table in CI, its results are turned to have value to the image GPS to 1, which is reflected its end, which increases to 1. Conclusion. As seen above, the NCI is an index that applied to priority communication and safety proposes 2 sub-indices. For example, priority in communication to the following entity can be dealt with quickly in scenario 2, where there was a failure in the mechanism, while an alert was issued to prioritize communication. There are GPS spoofers that has devices that create GPS signal files to trick receivers into thinking they are in a different location at all times. In this study, we used GPS spoofing, GPS location, an application for Android phones that falsifies the position by rewriting the location. The location indicated during the GPS was correct and was the initial smartphone, the city of Alegrete at 6 p.m. actual in this figure. A minute later, at 15:33, a GPS location, fake GPS application was changed Pará, located in northern Brazil, as shown in the figure. It was verified that 3DR solo are indicate that in Pará. It would have moved a distance 2,035 kilometers in 1 minute. However, no alerts to drone central commands were issued. Finally, implementation and validation. Both metrics were implemented in C++ language in hamster architecture. To validate these metrics, a test scenario consists of UAVs that authentication with their central unit and provide telemetry data. The public station requests the UAV data on a server. Communications and interface. Abstraction is implemented using TCP sockets. When connected to the station, the UAV sends its ID and a public cryptographic key. The station connects to the UAV in some way, creating a bidirectional connection. After the link is completed, UAV sends hack entity access with its authorization information. If the data was plausible and GPS is working correctly during the whole trip, the station responds with message entity access granted and presents the flight history. Otherwise, the CMU or CSU alerts the central station the GPS spoofing is taking place, as illustrated in this figure. Then, the station prioritizes communication through the Wi-Fi transmitters and informs the decision-making module that an action must be taken. This research two metrics, one to security and one for safety, coupled in the hamster architecture to detect GPS spoofing in UAVs. Thanks.
Well, another interesting work. This GPS attack problem is real and serious. Unfortunately, we cannot do questions because the presenter is not here, but I suggest that if anyone has questions, you can address to her email. So let's move on to the final paper from this section. This paper is entitled Towards a Double Hybrid VTOL UAV System. The presenter is Alisson Lucena. Alisson, do you prefer present or use a video?
Vídeo, por favor.
Okay.
In this work, we are towards a double hybrid VTOL UAV system. And this is a work done by Alisson Lucena and by me. The idea is to build a UAV that can do vertical landing and taking off. So for that, there exists several configurations in the literature. One of them, and the most traditional one, I think it is this one that uses 4 electric motors for the vertical propulsion. And then since the vehicle is in some altitude, just change to a conventional combustion propulsion and using a wing for that. Well, in our configuration, we intend to use a UAV like this one. Not that we have here just 2 electrical motors and 1 combustion motor as in the other model. And instead of having a horizontal plane in here, the 2 electrical motors are aligned with the wing of the plane. So we use a conventional flying wing. Of course, it has been designed according to the motors that we want to use, and the motors were all set for it after it was chosen. And it has this 3rd motor for making the horizontal flight after it changes the mode of flight. Not the 2 only motors. These motors together with the elevons are responsible for some motions of the UAV system. For example, if I want to screw left or right, we just have to put more or less power in one of these 2 electrical motors. Okay, note the elevon in here is down. So if we want for this UAV to go forward or a little backward, for example, for landing, or we just can move the elevons, in this case both of them, right to the front or to back, and it is going to have this forward or retraction movement done. The other situation is where we want to make rotations around the z-axis, yet in vertical flight position. In this case, we just need to put 1 elevon for each side, 1 to the front and 1 to the back, for example, would make it rotating counterclockwise rotation motion. If I do the opposite, it goes in the other direction because of the windy passing through them. Okay, the elevons are also used in the horizontal flight motion. In this case, for example, if I want to do a roll to the left or to the right, I just make them going into the opposite direction, one of each other. And I can do these 2 motions, rolling to the left or to the right. If I want for the wing to do a pitch motion, in this case, I have to move both of them at the same time, above or down, and then the flying wing will answer with a tilt or not. Okay, here is how it works for taking off and landing. For taking off, we just put the maximum of power in both electrical motor and leave the 31 on, however, without power on it, without gas coming to it. Once it gets up, then it's time to change flight position, so we can turn on, we can make put more power on the combustion motor and turn off the two electrical motors. So in this case, it can go forward, and as combustion has more autonomy, in this case, it could do some longer flights. Okay, after that, if we want, there is two situations. I could make it stop in vertical flight position, for example, for some reason that I'm going to show next, or it can do a landing. For landing, so we have to get back again to the vertical position. Once we get in that, the electrical motors are on and the other combustion motor is off. Then, in this case, the plane can go down. A problem that happens not only in takeoff but also in landing is that when the plane is at some 70 to 80 centimeters from the ground, it completely loses stability because of the windy conditions in here. There is no stability. So for taking off, this is not a problem because it just pushes the motor with the maximum velocity, and that's okay. But however, with landing, this might be a problem that we didn't study yet. We're going to do that after the COVID-19 outbreak. We can study this case in more detail, but we didn't do that yet. However, we got some landing already. Okay, this is how it operates. The other situation, as I told, is where I can stop the flight, stop the plane during the flight for doing some, I don't know, maybe I want to take a picture of some object, and then I get back again to horizontal flight position. Okay, we have chosen a wing with 1 meter and 20 centimeters. It has an area of 0.339 square meters and an aspect ratio of 4.28. The aerodynamic chord is of 0.26 meter, and it has a gravity center of 0.242 meters from one of the extremities. For the wing profile, we have chosen a symmetrical one because otherwise this would result in a force that could produce some instability, and we don't want that. We want it more stable as possible. So the symmetrical one is not unique. There are some wing profiles for that. For example, here we have studied the NACA 0012, the Epler EA6, and the S1012 profiles. From those that we studied, the NACA was the one which gave us the best performance in our simulations. And so we have chosen it as the wing profile to be used in our work. Here we show the architecture of the embedded system components. We use two electric propulsion motors, as I said before, with their controllers. This comes from an autopilot. The control comes from an autopilot that has two servos, and it has also another servo that which goes to the propulsion with internal combustion, which is the main that maintains the UAV for more time in flight. Okay, remember these two electric motors are used in situations of landing, taking off, and eventually if you want to stop during flight for doing some task. Here you can see the items with their characteristics, and this is the built wing that Allison has constructed. with here it has already rubber covering it, and the electrical and the other motor are on, and the components too. Okay, for the flight setting and tests, we have used the mission planning, and I want to mean that the system is ready for doing tests with autonomous flight. However, we didn't do that yet due to COVID-19 break, so we are going to do that after this time. By now, what we have done is flights with remote controlled, and also we were going to do after the break tests with autonomy. That means how long can this airplane go? Can this UAV go? Okay. During our tests with remote controlled flight, here we can show the transition from a vertical to a horizontal flight. It went good. And then in here, we can show when it gets back. In this case, it was changed at 9 meters of height, and here it's about 4 meters. With 5 meters of decreasing, it got stability again. We got to recover from the horizontal to the vertical flight. So we should have some 5 meters of height in order for this operation to be, and we are going to work in this yet. Also here you can see the landing of it, of course, in a place that does not hurt the UAV. So in conclusion, we have built a complete system that is ready. We are now building another one, a little longer, with a wing of 1.5 meters, and we are going to make some tests with this new one to see if you get more stability. And that's it. Thank you very much.
Thank you, Alisson.
Okay.
Congratulations for your work, for your team. This is a really, really nice work, and should I confess that this is a kind of subject that really takes my attention. I know how it's difficult. So the first question is more a brainstorm. What do you think that is the main advantage of your configuration of this VTOL?
Desculpa, só vou te pedir para fazer a pergunta em português, por favor.
Desculpa.
Não,
então,
eu te pergunto, desculpa.
Essa primeira pergunta é mais assim, para a gente trocar uma ideia. Qual seria a vantagem dessa configuração do seu VTOL?
A matriz energética aos motores elétricos, ela é consumida muito rapidamente, né? Alguns testes a gente consegue aí em torno de 15 a 18 minutos de voo só. Então, com o mesmo peso de combustível, eu consigo um voo com autonomia bem maior, né, de tempo. Então, quando eu utilizo o motor a combustão, eu consigo atingir grandes distâncias, né, e não tenho necessidade, vamos dizer, de uma pista, né, de decolagem, essas vantagens aí.
Perfeito. Agora uma outra pergunta. Qual é a estimativa de alcance do seu UAV?
Esse é um protótipo, né? Então, a intenção, primeiro, era conseguir voar, né? Colocar ele para voar na parte híbrida. Mas com a configuração que ele está aí agora, ele consegue, com asa voadora, em torno de 40 minutos, essa configuração. E na parte, no voo elétrico, né, no voo multirotor, é nessa faixa aí, uns 15 minutos. Varia um pouquinho dependendo da condição do vento.
Só a última pergunta aqui, porque eu vi que vocês estavam testando, corajosos, testar já em um ambiente ali real, né? Vocês testaram essa questão de de alguns distúrbios, por exemplo, de vento, quando vocês estão fazendo take-off?
Sim, sim. O maior problema que a gente tem enfrentado é o vento quando ele está diretamente na asa. Quando a asa está alinhada com o vento, eu consigo que o vento atravesse, né, a aeronave e não desloque ela. Mas quando ela bate, por exemplo, na parte superior da aeronave, então ela desloca muito na parte na hora do pouso e da decolagem. E outro problema que a gente tem também é a parte do efeito solo na hora da decolagem. Na hora da decolagem até nem tanto, eu consigo acelerar e aumentar a velocidade de decolagem e não sentir tanto, mas na hora do pouso...
Do take-off realmente pior, né?
O fluxo que vem dos motores elétricos, a partir de 60 centímetros, começa a desestabilizar a aeronave. Mas nada que comprometa muito, não. Mas precisa ser corrigido, sim, essa parte. Aqui
muito
em Natal,
obrigada.
Agosto é a época dos ventos, né? Então, os testes em agosto são complicados. Mas
imagino.
Teste bom é teste ruim, né? Quando as condições estão complicadas, a gente consegue uns bons testes.
Também é resultado, né?
Isso é.
Muito obrigado, Alisson.
Eu que agradeço.
So I want to say thank you for everybody to watch this section, and this was the last paper from this section. So we can move on to the next section. Thank you, everybody.
Thanks, Milena.
Hello, are you guys listening?
It's okay, Daniel.
Okay, so good, thank you. So hello everyone and welcome to the next section of Assistive Robotics and Human-Robot Interaction number 3. I am Daniel Tosadori, a PhD from University of São Paulo, ICMC. I'm here on behalf of Professor Roseli Romero. She was supposed to present this section as chair, but she had a little unexpected situation and asked me to be here, so which I'm doing with a huge pleasure and honor. So as you all know, we are having three presentations this section, and the presenters will have 10 to 12 minutes to present, and after that we can ask questions. If you are watching from YouTube, you can insert your comments there and we are reading it as well. So feel free also to contact the authors in the contact they will give in their presentations. So starting with the first one, actually three very interesting topics, to be honest. And the first one is a simulated environment for development and validation of an inspection robot for confined space. Who is presenting is André Siege, is that right?
Yes.
Okay, so welcome, André, and
thank you.
You can take control from here.
I would like to ask the chat to run my video, a presentation, because my internet is a little unstable, so I can lose my connection at any moment. So if you can...
Sure, no problem.
Presentation.
Okay, I will present it. Just a second.
Thank you. Hello, my name is André Siege. I'm an undergraduate student at the Universidade Federal de Ouro Preto and I intern at the Instituto Tecnológico Vale in the research project of the Espelho Robô. I will present a work entitled A Simulated Environment for the Development and Validation of an Inspection Robot for Confined Spaces. These are the topics present in this work. Introduction. Thanks to technological advances, the use of robots is increasing for the most diverse tasks. Among these, inspection and mapping services are always required, especially in areas not suitable for human occupation, such as confined spaces. There may be a risk of collapsing these places, poor ventilation, toxic gases, venomous animals, among others. Therefore, the best way to reduce risk is to get people out of these dangerous places. So, the use of robots, teleoperated or autonomous, increases this task safety. However, confined environments are also challenging for robots due to low lighting and visibility conditions, lack of global positioning, uneven and slippery terrain, and sensor interference. These environments are so challenging that DARPA's U.S. Defense Advanced Research Projects Agency newest challenge focuses on the inspection of confined environments like caves and underground mines, the DARPA Subterranean or SUBT challenge. Considering the robotic platform, there must be a suitable place to carry out possible operators training and even test algorithms, software, and hardware without putting the robot or other people at risk. Therefore, the use of an appropriate robotic simulator is critical. Among the various simulators available, one that is compatible with ROS is needed to do it to its modularity and also because the real robotic platform uses the system. It is also necessary to have a physics engine to ensure greater fidelity to the real scenarios. With physics engines, simulators can represent realistic interactions such as weight, friction, effort, and other characteristics of static and dynamic objects. As seen in the video, caves and mines have an uneven surface. Focusing on confined spaces, the simulator must allow the use of single mobile robots in large detailed environments. A reliable representation of the environment is modeling and editing of ground mobile robots, support for several sensors, and raw support. Among these topics, 3 simulators fit the requirements: Argus, Gazebo, and Coppelia Sim. While Argus is geared towards simulating robot swarms, Gazebo and Coppelia are more appropriated for large scenes and just one robot. Coppelia stands out due to the permission to change models, robots directly, and great fidelity of dynamic interaction. Simulated environments. Vale S.A. developed the Speleo robot for inspect and map confined spaces. The robot can drive with wheels, star-shaped wheels, legs, tracks, and hybrid configurations. Quick-release pins allow for easy and fast exchange of multiple locomotion systems. It can also be equipped with an instrumented tower with several sensors to perform 3D mapping and other inspection tasks. In this video, we can see Speleo robot conducting an inspection at the Veloso mine in Ouro Preto. In the image on the left, you can see the real robot, and on the right, the simulated robot. The robot is equipped with 6 sets of planetary reductions, MCD EPOS motors from Maxon Motors with encoders and drivers already integrated, a pair of axis cameras with high brightness, and LED lighting. To represent the robot reliably, some sensors made available by Coppelia were used, such as lighting, front and rear cameras, engines, accelerometer, gyroscope, and depth cameras. The environments that will be used by the robot can be adapted from the real world through computer-aided design to facilitate the import of objects for simulation. Another way is to use reconstructions. Such reconstructions can be performed through LiDAR or photogrammetry. The scenarios reconstructed by LiDAR have high fidelity in form, but they lack texture, while photogrammetry requires only images acquired by ordinary digital cameras, and the reconstructed scenes has real textures. In this image, we can see the inside of a real ball mill. In this one, the same mill was designed for the simulator through computer-aided design. Here, the mill was reconstructed using a LiDAR. The first image is a motocross field with RGB texture of the real field, reconstructed using photogrammetry. The second image is the reconstruction of a gold mine by fusing data from a LiDAR and RGB cameras. The third image is a ball mill designed in SolidWorks and exported to Coppelia Sim. And the last image is an underground map provided by DARPA. Evaluation of the simulated environment. When it comes to the simulator's performance, it is essential to consider a trade-off between efficiency and accuracy. Simulations with many dynamic interactions or a large number of sensors and actuators require more processing. The real-time factor is used to analyze the simulation's efficiency in different scenarios, which corresponds to the relationship between the simulator's time and the real time spent. To analyze the dynamic model of the robot, 3 maps are used with different numbers of faces, where the greater the number of faces, the greater the number of dynamic interactions. The first model is the most detailed, in order to maintain a shape very close to the real robot. The second model is a simplified one, with reduced number of faces. The third is composed only with pure geometric shapes, ensuring less processing of the simulator. As shown in the graph below, very detailed dynamic models dramatically alters the simulation response time in complex maps. Although the detailed model is necessary in some specific cases, the simplified model does not show any substantial difference in the robot's performance. Thus, the simple model proved to be more suitable for most operations. In this graph, we can see the impact caused by the sensors in the simulation. Considering each sensor's performance, it is possible to use only a few sensors required for each simulation, or even change the frequency of data acquisition and processing. For example, it is unnecessary to use Velodyne if the objective is only to train the teleoperation. Still, RGB cameras need high frequency to guarantee the fluidity of the teleoperation. On the other hand, in mapping simulations, the camera do not play such an important role, and they can have their frequency changed or even disabled. Another way to optimize sensor is through plugins. Such plugins allow data processing outside the simulator. A C++ plugin was used to improve Velodyne's performance in Coppelia Sim. It is possible to notice a significant improvement in the simulation when this plugin was used. In this image, we can see the teleoperation interface used by SBR robot. This interface allows the operator to monitor important information about the robot, such as motor's current, speed and status, distance traveled by the robot and options for recording inspections, LEDs information as well as turning them on and off, options to change the movement direction of the robot, and front and rear camera images. In this image, it is possible to see the interface adapted for the simulation, containing the same information presented in the interface of the real robot, with only a few additions that were first implemented in the simulation, such as collision alert, stability, and quality of the communication signal. The simulation also allows the analysis of the robot's mobility and stability in environments before submitting it to a location with a possible risk of overturning. For such tests, it's good to use the more detailed dynamic model to ensure that it behaves more closely to the real world. In this video, a manual test is performed first and then a simulation of the SBR robot in a ball mill. Here we can see the mapping process performed by merging data from LiDAR or depth camera with other sensors like inertial measurement unit and odometry data. This allows for simultaneous localization mapping technique, SLAM, and the octomap is used as the basis for the map reconstruction. Then, the 3D mesh of the environment is treated as a graph. Edge weights can correspond to different metrics, such as distance travel, terrain transversality, energy consumption, and combined metrics. We presented a methodology for the simulation of terrestrial inspection robots in confined spaces. The simulated environment allows the validation of experimental algorithms and operator training without damaging the real platform or placing operators at risk. Experiments demonstrate the advantages of using simplified dynamic models in the simulation. The simulated sensors' performance for different virtual environments was also presented, showing the advantages of using external plugins for the most CPU-intense sensors, such as LiDAR. Finally, a mapping path planning and control pipeline is described, which works entirely with the simulated environment and can also be used in the real robot. Future work will focus on validating more simulation parameters and sensor configurations, including different physics engines, and evaluating new navigations and control algorithms. Environments for cooperation and collaboration with other types of robots will be also evaluated. Thank you.
Very nice work, Andrea. Congratulations for you and all your colleagues. And do we have some questions from YouTube or someone that is watching here in Zoom? Okay, so I have. You said that you searched for a trade-off between efficiency and accuracy, right? So by efficiency, you mean the time, the computational time that you were evaluating, or something else? Because accuracy, if it was the right choice about the path that the robot was following, right?
The accuracy in this case was how likely to the real world the robot will guarantee the perfect behavior, okay. but it's a fluid simulation. The operator can use the robot, it will not feel any pretty slow, depending on the sensors and the map.
Okay, so great results, huh? Congratulations again. I'm excited to see this happening in a real world environment, because there is a large breach between these both conditions, and I bet you face a lot of challenges doing so. But congratulations again to you and all your colleagues. And we are moving on to the next presentation, which is, this one. If you deal with robots in your life, you ask this question to yourself at some point, because we are talking about security on ROS, analyzing and exploiting vulnerabilities on ROS-based systems. And well, if you are running simulations, or if real world experiments, you use it ROS in your life. So that's the question everybody is excited to see what is the answer of all this topic. So who is presenting this is the I think
it's me,
Rafael Teixeira. So welcome, Rafael.
Yes. Thank you.
So are you presenting live?
No, I have the video.
Okay.
Rafael, I did not receive the video. Can you put on the chat? Is there a link? Is there a link from Google Drive?
Just 1 second.
Julio?
Yeah, Bruno.
Can you hear me?
Yeah.
I just uploaded the sheet with the video. With the video.
Okay. So I'll just play it.
Okay, you can take control from here.
Hi everyone. My name is Rafael Teixeira, and this is the presentation of my paper called Security on ROS, Analyzing and Exploiting Vulnerabilities of ROS-based Systems. I am a computer engineering student at the Federal University of Rio Grande, and I've been working with robots since the past 3 years as part of the FBOT team, which is a team that develops robots for competing in the RoboCup events. The goal of this paper and presentation is to expose some of the vulnerabilities found on ROS and what kinds of impacts can a malicious user have on the robotics system when exploiting these vulnerabilities. So the last decades brought very important advances to robotics in general, from artificial intelligence to speech recognition. Advancements in control, navigation, mapping, and other important topics are improving the development and the usage of robots in our everyday life. And since humans and robots are sharing increasingly more environments, it is important to keep cybersecurity in mind when developing robots. The Robot Operating System, ROS, is one of the most adopted frameworks in research and development of robotics, even though it has a lot of security issues. According to the official ROS website, there's around 22,000 active members in the ROS community, more than 5,000 software packages available for the official ROS distribution, and 140 commercial robots that support and use ROS as its main communication framework. Also, there's 4,800 research papers that cite the usage of ROS. Alright, so how does ROS work? From a communication standpoint, ROS is a peer-to-peer process network composed of a ROS master, ROS nodes, messages, and topics. The ROS nodes are simply processes running any kind of computation, that communicate with each other by sending messages on topics, and the ROS master is a node that is responsible for managing the connection between other nodes. The communication between the ROS nodes and the ROS master is made by an XML RPC protocol. In this type of messages, nodes can either advertise to topics that they're sending data on, or subscribe to available topics on the ROS network. And as this graph shows, here we have a scenario where a node called Hokuyu advertises a topic called scan to the ROS master. In the second moment, a node called viewer subscribes to this topic, and then the ROS master is responsible for informing the viewer node on which port the Hokuyu node is expecting a connection. So now the viewer node can talk directly to the Hokuyu node, and a TCP connection is established between the two of them. And it's through this TCP connection that the data is actually sent. So in other words, ROS nodes can either be publishers or subscribers, and the role of the ROS master node is to manage the communication between publishers and subscribers. So it is important to define what actually makes a system secure, and for that there are the three pillars of information security, which are confidentiality, integrity, and availability. The principle of confidentiality refers to being able to create certain access level for the information that you're sending on a network. So, in a network of communication, an unauthorized party cannot be able to read a message that was not intended for them. The principle of integrity refers to the actual content of data trafficking in a network. And to guarantee integrity, you must first assure that a message cannot be changed or blocked when trafficking through a network. Now the final component of these three pillars is the availability. In this case, the system must always ensure that the data will be available whenever it's needed. Now, having these three principles in mind, we can start to talk about the ROS security issues. So in terms of architecture, a publisher-subscriber model, by definition, allows any network agent to interact with any topic, allowing any malicious user to monitor and even publish fake messages in the ROS network. There's also no default type of authentication involved in ROS, so every network user is treated as reliable and therefore can interact with any other ROS nodes. Every ROS topic has a predetermined message type. Message types are basically a data structure that defines the format on which data will be sent on this topic. However, there's no validation implemented in ROS that guarantees that every data sent on a topic is on that predetermined format, which means that a malicious user can send packets of data on a valid ROS topic that is not on the format that the subscriber is expecting. And with no validation, these packets of malformed data will be considered a full irreliable message. ROS also does not implement by default any type of cryptography on its topics, so there's no confidentiality at all in the messages that are being sent on the ROS network. So any user and any valid network agent can read the data that's being trafficked between two nodes. This brings us to our case study. The vulnerabilities of the architecture and the communication mechanisms used by ROS allow us to develop a tool that can exploit and compromise any robotic system that uses ROS as its main communication framework. And by exploiting the aforementioned vulnerabilities, we can break all the three pillars of cybersecurity. Our research group is developing a robot named Doris, and Doris was made to compete in the Robocop at Home category. Doris is a robot made to be used in household environments. It is able to navigate, recognize people, and even interact with real-life objects. So we developed a tool that is able to compromise Doris' main communication framework by exploiting ROS vulnerabilities. One of the main components of Doris is an external processing server connected to the router that is attached to Doris' body via wireless connection. And Doris is sending data to the wireless connected server via a ROS topic. So our goal here is to try and exploit the ROS vulnerabilities in order to try and intercept and read and even alter the content of the messages that are going from Doris to the external processing server. So on a closer look to this communication, we see that Otis runs a ROS node called speech-to-text. The robot captures voice commands from the environment, parses these voice commands into a text form, and publishes this text into a topic called speech-to-text. So our processing server runs a subscriber node that reads the data from the speech-to-text topic and processes this text in order to define the command instructions that will be sent back to the robot. So a third computer in the network runs the application that we developed to intercept and to alter the messages that travel between the robot and the processing server. The attack happens on a three-step process. The first step is to map the network in search of the IP addresses of Doris, which runs the publisher node, and the processing server that runs the subscriber node. Once we know these IP addresses, we can perform an attack called man-in-the-middle. And this forces all the messages intended for this ROS communication to pass through our attacker computer. And once the messages are redirected to the attacker computer, we can apply network filters to gain control over the content and the availability of those messages. Now, there is a lot of techniques that can be used to perform a man-in-the-middle attack, but the one we've chosen for this application is called ARP poisoning. The Address Resolution Protocol, or ARP, is a network protocol that maps Ethernet addresses to a physical address. In other words, it links an IP address to a network MAC address. And by exploiting the usage of the ARP protocol, we can force the processing server to map the robot's IP to the attacker's computer MAC address. And also, we attack the robot to force it to map the server's IP into the attacker's MAC address as well. And by forcing this unintended IP to MAC mapping on the network, all the targeted messages are sent to the attacker's computer instead of their original destinations. So here we have an illustration of how that man-in-the-middle attack process is happening. First, our attacker computer sends to the server an ARP packet that tells it that the IP address of the robot is physically located at the attacker's MAC address. So now, any packet intended for the robot's IP will be physically redirected to our attacker's network interface. And then we do the same for the robot. We send an ARP packet that informs the robot that the IP address of the server is physically located at our attacker's MAC address. So any messages from the robot to the server's IP will be physically redirected to our attacker's computer network interface as well. Okay, so we have the three steps of the attack process. First, we map the network, then we perform the man-in-the-middle, and we apply network filters in order to manipulate the packets that are going from the robot to the processing server. And to automate that task, we develop a Python script that is developed to coordinate the attack stages. And this makes the attack more customizable and automated. And now that we are intercepting all the data, we can change the informations by implementing a function that is called whenever a message arrives. And in this way, the attacker can visualize, change, and even interrupt completely the communication between the two ROS nodes. Also, our experiments show that altering the data trafficking between these two nodes into a format that is not expected by its subscribers, we can force a segmentation fault on these nodes. So we can not only alter the data that's trafficking on a ROS topic, we can even force the ROS nodes to stop completely its execution. So the development and experimental success of the attack script shows that even though it's largely adopted, ROS has huge security issues. It is extremely dangerous to have ROS-based robots in human-robot shared environments, once you can guarantee, by default, the security of the system. There are some solutions that can be implemented to further improve the security of ROS-based robots. One of them is the implementation of cryptography on the ROS topics, but that usually comes with a trade-off. In this case, you can't have a real-time communication if you're cryptographing every single message. So it is not trivial to implement even the more basic forms of protection. When sometimes you can simply sacrifice real-time communication when you're working with a robot that shares the environment with humans. So I'd like to thank you all for your time to watch this presentation. And here's my contact info in case you need to ask me anything, or even talk about the problems exposed here. Thank you all, and have a good day.
Wow, it's such a important topic, and I think if we are considering trying to insert robots in our home, this is a crucial issue, right? Because security it's something mandatory if you want to share our home space with robots, I think. So it was a very informative presentation as well. And do we have some questions from the attendees or audience? Okay, no question.
Hi, Daniel, I have a question.
Okay, Bruno, please go ahead.
Thank you, Rafael, for your presentation. Very informative, as Daniel said. I wonder, I do not know ROS version 2 very well, the newer version of ROS. And I was wondering if ROS 2 provides some form of protection or some counter measures against, that could provide a protection for network attacks, as you said in the presentation.
Well, hi. Actually, I haven't studied a lot of ROS 2 because it's not officially released yet. So the main focus of this research was on the official distribution of ROS. But I have seen a few discussions on the internet about ROS 2, and it still does not have a full security implementation. It still has no cryptography or any validation of the messages. There's still a lot to worry about, even when using ROS 2.
I had another small question, if I may. I was thinking about the cryptography meanwhile you were doing the video presentation, and at the end you say it. So do you guys already have some notion or some measure about how much would be the loss of the efficiency when you do this cryptography in the message, or is it just a future study?
This is mainly a future study, but the actual implementations of cryptography on ROS usually impact the real-time nature of this communication. So when we are working with robots, especially the ones that share environments with humans, we cannot sacrifice the real-time nature of this communication by using the cryptography. So the current implementations of cryptography on ROS are still not a good idea when you are working with real-time environments.
I see. Yeah, so lots of work to perform in the next ROS.
There's a question from YouTube.
Okay, please tell it. Okay, a question from YouTube. Diego Pereira said, in this case, is the attacker authenticated on the network or if something outside the network?
No, in our experiments, the attacker was a valid user on the network.
Okay, so...
Yes.
Okay, so thank you for this amazing presentation and well-covered topic. And so we are moving on to the next presentation. That will be a Brazilian Sign Language video dataset for automatic recognition. And who will present it is Wesley Passos. So Wesley, are you presenting live or do you send the video?
Yeah, I have sent the video, so I'd like to ask you guys for playing that, please.
Sure. No problem. Just a second.
Hello, I am Wesley Lobato Passos from Federal University of Rio de Janeiro. I am here to present the work, a Brazilian Sign Language video database for automatic recognition, developed in collaboration with Priscila Gameiro and professors Gabriel Araújo, Amaro de Lima, Jonathan Góes, and Ana Corbo from Cefet, Rio de Janeiro. We begin this presentation by mentioning the motivation of this work. Also, we briefly talk about some approaches in the literature. We then describe the dataset developed in this work and go into some details. Afterwards, we show an approach to automatically recognize gestures. Finally, we present the experimental results obtained that may serve as a baseline for our dataset. The presentation ends with our conclusions. Communication is a basic human necessity, and the spoken language is a more common way to establish a conversation. However, the deaf community is still facing some barriers. In Brazil, there are about 9.7 million people with some degree of hearing loss, which corresponds to about 5% of the whole Brazilian population. Among these, only 15% are fluent in Brazilian Portuguese. Besides, most Brazilians don't know the Brazilian Sign Language, also known as LARS. Therefore, the development of an automatic tool may help these people to establish communication. In the literature, there are two main approaches to recognize gestures. The first one uses some device such as colored gloves or sensors to easily track the movements. The disadvantage of this approach is that the sensors can limit the movements, turning the communication uncomfortable. The second way to extract the information of the gesture's movements is using computer vision. This approach is also known as pure visual-based gesture. This type of approach is less intrusive, using only cameras. However, the usage of computer vision is more challenging. It may lead to a lot of unrecognized gestures. Most of the works in computer vision focus on static symbol recognition, which no movement is considered. In this case, the database can be constructed using only image instead of videos. Moreover, there are many databases for other language, for example, American Sign Language, but only a few of works consider LARS. Therefore, in our work, we developed a video dataset composed of dynamic gestures that may be used to train artificial intelligence algorithms that may be implemented in robotic systems, for example. We also propose a computer vision approach that may be used to recognize gestures. Our database consists of 547 video sequences and 24 words. The video sequences have 640 by 480 pixels as resolution at 30 frames per second. The records were done in a controlled environment in 3 different static backgrounds. Each entry was performed by 20 non-deaf volunteers, being 13 women and 7 men. This database is available under request. The gesture sequence is performed in a video that describes a word entry. This table shows all entries presented in our database and their respective acronym. It's important to mention that the acronyms make sense in Portuguese. Also, it's possible to segregate the entries into 2 classes, the first one with horizontal hands movements and the other one with the vertical hands movements. All the information about acronyms, background, and volunteer identification is contained in each video file name. Following, we present some statistics of our database. This figure shows the duration distribution of the videos in the dataset. It's worth mentioning that the longest and the shortest videos of the dataset have 134 frames and 14 frames, respectively. The average length of the video is 50.05 frames. This slide shows a general information about the number of occurrences of the words in the dataset. The frequency of the words spoken by volunteers is presented in the most left figure. The most right figure shows the total number of frames for each word. We also analyze the distribution of the volunteers in the database. The most left figure shows the occurrence of each volunteer in the dataset as a whole. We can notice that the volunteer ID 04 appears a lot and the ID 17 is a bit shy. From the center figure, it is possible to observe the distribution of the volunteers in the backgrounds. It tends to be balanced if we consider the same volunteer, with exception for volunteers ID 03 and ID 40. We also analyzed the number of times that each volunteer has spoken each word. As we can see from the most right figure, the maximum number of times that the same volunteer repeated the same word is 3, which corresponds to the 3 different backgrounds. Also, Some volunteers did not have spoken some words. We now describe the proposed method to recognize Libra signs. This was done to validate our database and to serve as a baseline for future works that intend to use our dataset. First, each video was resized to kill by kill using bicubic interpolation. This was done to minimize the complexity. Next, we performed feature extraction. The feature extraction consists in mapping the video frames into a feature space that we called squared residue. The mapping is given by this equation here, where IN is the nth frame in the video sequence. This feature extraction is the sum up of the square difference between the frames. After that, we perform the classification. In this work, we use multi-class KNN or random forest classifiers in a MATLAB implementation. We performed grid search for the number of trees, optimization of the random forest classifiers. This pipeline is illustrated here as a block diagram in this figure. So now we are going to present our results obtained. First, it's important to mention that we validate our results using k-fold cross-validation with k equals 3, so that all the results are the average across the folders. We performed experiments varying KO. The most left figure here shows the results when using k and n as a classifier. For this classifier, we ran our experiments into two versions of the dataset, one with considering only 12 words, and the other with the whole dataset. One can note from the graph here that the accuracy drops when the number of words are increased. The KNN is a simple classifier which probably could not handle the increase in the problem complexity when more words are taken into account. The most right figure here shows the performance when using random forest and varying the number of trees. Random forest is a much more powerful classifier when compared to a KNN, so it could handle better with the full database. This table summarizes all the best results obtained. The results here in the first line is considering only the absolute frames difference. When using KNN as a classifier, there is no significant difference between absolute and square residue. In all cases, the accuracy drops when the number of words increases. However, when using squared residue with random forest as a multi-class classifier, the accuracy remains satisfactory, achieving an average accuracy of 87.23% across 12 classes, using Q equals 5 and 300 trees. Also, we can achieve 65.81% across the 24 classes when using Q equals 50 and 400 trees. So, in this presentation, we showed what has motivated this work. We also presented some approach in the literature. Next, we described in detail the LIBRAS dataset, which is a challenge database with 547 videos with 24 dynamic signs. To serve as a baseline, we developed a computer vision-based system to recognize the gestures. In the proposed system, the feature mapping is performed by summing the squared residuals video. This feature space can capture the LIBRAS details such as the face, hand configuration, as well as motion. The gestures in the feature space were classified through KNN or random forest. In the k-fold cross-validation framework, we achieved an average accuracy of 65.81%. Due to the complexity of the database, we consider it a satisfactory result. We observed that technological tools for sign language are very important to diminish the communication gap between the deaf community and the majority of the people. Tools using computer vision may be very powerful. I really appreciate your attention and look forward to answer any questions that you may have. Thank you.
Well, such a noble application. Congratulations for you, Wesley, and also your colleagues.
Thank you.
I'm pretty sure you're having a large of enormous headache because you have to deal with a lot of features to extract and also perform all this validation. And did you consider compare with another algorithms as well, such as CNN or also another classification algorithm?
Yeah. Actually, there are this work is a part of a big project. So
Okay.
we have more. We are constructing a larger data set. So, and the idea here is to use something that may be simple to serve as a baseline. So actually, we are kind of finishing our work that we use convolutional neural networks to extract the body parts of the people, so that we can use that as an information for a classifier.
Well, congratulations again. Is this data? Sorry, is this data set available for whoever wants to use it?
Not everyone. Actually, it's available on the request. You have to email the professor Ana Regina. So it's only because of the intellectual properties. I don't know if it's the right choice. So you have to send an email to her and asking to use the data set.
Okay, in any case, someone can send an email to you and then you can redirect for this person you said, okay? Is that correct?
Sure.
Okay.
Yeah.
Okay, so do we have
There's a
questions?
question on the audience, I think. Marcelo Tasso.
Ok.
Já pode começar?
Yes, please go ahead. I think your microphone is closed.
Yeah.
Okay.
Oh, okay. Maybe he mistook Tasso.
Okay. Okay, Tasso, we had a miscommunication here. So you are the next presenter, right? And we did not finish the last one yet. So you are coming up next. Okay. Tasso, can you hear me?
Yeah, I'll try to close this screen share. Okay, so you can proceed.
Okay, so do we have some other questions to Wesley? Great. I think we are out of time already. So thank you again, Wesley, and congratulations for you and your colleagues for your work. So I think we are done. I would like to say thank you to all the authors for all the amazing works. It was it was my pleasure to see this. I wish my best wishes for all these works that have been presented here during the session. And thank you all for your attention, guys. And from now on, I'm handing over to the next session chair, who is already here, right? Hello, Pablo.
Hello, Daniel.
So
thank you very much.
Thank you very much. Okay, thank you, guys. Thank you, committee. Organize.
Ok, let's move to the next session.
Eu consegui arrumar. Eu acredito que não está saindo áudio, né?
Yeah, I can hear, Professor.
Okay.
Tasso, we'll mute your microphone because it's not your time yet. So, and it's it. Professor Pablo will tell it.
Okay, good afternoon. I am Pablo Alcina, and I will help you in the next section. that is called Vision Sensing, Mapping, and Path Planning, section 5. So we have 4 interesting works, and we will begin with Tarcio. Okay, Tarcio, with the paper System for Recognition of Facial Expressions using Machine Learning. Okay, Tarcio, you're welcome. You're in control. Tarcio, are you hearing me?
Isso, agora eu tô ouvindo. Isso, tô
Okay.
ouvindo. Uhum. Ok. Só um momento. Bom, acredito que agora tá tudo ok, né?
Yes.
Certo. Boa tarde. Eu irei apresentar o artigo Sistema para Reconhecimento de Expressões Faciais, utilizando Machine Learning. Somos 3 autores, eu, Thales Almeida Silva, estudante da Universidade Estadual do Sudoeste da Bahia, UESB, Natália Pinheiro da Silva, também estudante da UESB, e a coordenadora do projeto, professora doutora Alexandra Oliveira Andrade. Para adentrar na apresentação do artigo e projeto, eu irei falar um pouco sobre o que nos inspirou a produzir este artigo, que foi o aplicativo chamado Webot. Ele é uma inteligência artificial que foi desenvolvida pela Universidade de Stanford com um respaldo científico muito grande, pois em sua base de pesquisa tiveram psicólogos, estudiosos da área de interação humano-computador e até mesmo médicos psiquiatras. O lançamento do aplicativo teve muito sucesso, possuindo milhares de downloads e comentários positivos, dizendo que o aplicativo mudou a vida das pessoas e pedindo até tradução para outras linguagens, visto que o app só está disponível em inglês. Falando um pouco sobre o desenvolvimento e o objetivo, ele teve o intuito de tornar a saúde mental das pessoas mais acessível, a partir de um aplicativo, né, onde o usuário poderia utilizar para ter conversas direcionadas a respeito de algum problema que ele esteja passando no momento. Desde problemas pequenos, envolvendo discussões, etc., até problemas mais complexos, como ansiedade e depressão. Nesses casos mais graves, o app até recomenda ao usuário a procura de um profissional da saúde, visto que o aplicativo vem como uma forma de complemento da saúde mental e não um substituto do profissional da saúde. Falando um pouco também sobre a implementação do Webot, ele está na categoria dos chatbots. Os chatbots são um tipo de inteligência artificial que é capaz de dialogar através de respostas digitadas ou faladas pelo usuário, que são dados como entrada para que a app possa retornar uma resposta de acordo com o que o usuário escreveu. Porém, mesmo com todo o sucesso do Webot, ele acaba possuindo alguns ruídos em suas respostas, visto que ele não possui contato visual com a pessoa que está dialogando, e dessa forma, palavras soltas às vezes se perdem no contexto sem a existência de uma expressão facial para que possa significá-la. Inclusive, fazendo analogia com os profissionais da saúde, existem evidências que a separação física entre o profissional da saúde e o paciente nas consultas pode comprometer a riqueza e a complexidade de detalhes fornecidos. Então, detalhes como contato visual, o olhar, as expressões faciais e pistas no geral que o paciente poderia deixar, por exemplo, para um profissional da psicologia e que poderiam modificar o significado do que foi dito pelo paciente, se perde na riqueza dos detalhes que o contato visual poderia fornecer. E foi pensando em como o Webot, mesmo com as suas limitações de não ter o contato visual, que melhoraria sua fluidez e resposta ao usuário, e mesmo assim pode ajudar tantas pessoas pelo mundo, surgiu a ideia da Rio, que é unir o chatbot a uma inteligência artificial de visão computacional, de modo a contextualizar as conversas a partir das macroexpressões faciais, ou seja, além do processamento de texto, é feito um processamento de imagem que retira da imagem as macroexpressões faciais predominantes do indivíduo naquele momento, e dessa forma se pode utilizar tanto os dados fornecidos via texto ou voz pelo usuário, como também os dados fornecidos pela análise da expressão facial. E com essa maior riqueza de detalhes, o sistema aumentaria sua porcentagem de chance de acertar o sentimento ou a interpretação do que o indivíduo tentou expressar para a IA. Isso foi pensado, pois atualmente não existe uma inteligência artificial que realize o processamento de imagem, voz e texto e une os 3 tipos de aprendizado para melhorar a interação e resposta ao usuário, sendo que foi feito um recorte e o processamento de voz e texto é um ponto a se incluir em uma versão futura do projeto. Para este projeto, o recorte foi feito focando somente na visão computacional da nossa IA. Futuramente será por si só multissistema. E atualmente, por ser portável e de fácil acesso a outros sistemas, o seu propósito é cooperar com os tipos de aprendizado, diminuindo o ruído e complementando o aprendizado desses outros sistemas. Para que a RIO fosse produzida, foi utilizado a CNN, que são redes neurais convolucionais, que tendem a demandar um nível mínimo de pré-processamento quando comparado a outros algoritmos de classificação de imagens. E foi por isso que a gente fez essa escolha. Para o reconhecimento das expressões, foi necessário um grande conjunto de dados. O que foi utilizado é o FER 2013, que é um conjunto de dados open source, consiste de 35.887 imagens de faces em tons de cinza, em 48 por 48 pixels, com um total de 7 emoções, todas rotuladas. São essas raiva, nojo, medo, felicidade, tristeza, surpresa e neutro. O rosto nas imagens foram registrados automaticamente para que a face fique o mais centralizada possível e ocupe aproximadamente a mesma quantidade de espaço em cada imagem. Bom, falando um pouco da escolha do recorte, por que começar pela visão computacional e não pelos outros campos? Isso porque, ao analisar uma expressão exibida por um indivíduo, é possível se obter várias informações sobre ele, seu estado emocional, se está com fome, entre outras várias propriedades que possam interessar, depender do fim. E sabendo da importância das expressões faciais para um diálogo ou interação qualquer, buscamos explorar isso também no campo da tecnologia, já que hoje existem várias formas do ser humano de se comunicar com um dispositivo tecnológico, seja através de celular, computador, televisão, entre outros. Porém, muitas vezes essa comunicação pode não ser tão receptiva por parte dos dispositivos, já que o tempo todo eles estão apenas recebendo comandos e retornando algum resultado, sem saber se tais resultados estão sendo satisfatórios ou não para o usuário. Então, seria possível os dispositivos tecnológicos saberem o nível de satisfação do seu usuário sem precisar perguntar a ele? A resposta é sim, através das expressões faciais que o usuário está demonstrando enquanto utiliza o determinado sistema. O que motivou nossa escolha para iniciar por esse campo é essa implementação de reconhecimento de expressões faciais por parte do dispositivo tem muitos benefícios, tanto para a ciência, como foi feito com o Webot, né, com a aplicação mais científica, como também para aplicações comerciais. Certo. O objetivo de cruzar os dados entre os sistemas para melhorar a resposta que irá ser exibida ao usuário tem o sentido de que um dado solto é somente um dado, porém dados de outras fontes cruzados e classificados se tornam informação. E baseado nessa premissa, o projeto teve o propósito de produzir essa inteligência artificial que é capaz de reconhecer macroexpressões faciais e retornar essas macroexpressões para o sistema ou qualquer outro dispositivo tecnológico que a implantou. Dessa forma, ela pode atuar tanto como um subsistema, como sistema principal, a depender do propósito. Várias empresas podem tirar proveito da reação dos seus clientes ao utilizar os seus produtos. Essas empresas podem ser restaurantes, por exemplo. Enquanto uma pessoa almoça, irá ser analisado se ela está gostando do que está vendo no cardápio, da comida que está comendo e até mesmo do atendimento do balconista. Lojas de acessórios podem saber se os itens da loja estão devidamente categorizados e, observando a expressão de confusão no rosto dos clientes, pode melhorar essa questão da categorização dos produtos. E até mesmo carros inteligentes que podem analisar a expressão do motorista e saber se ele está com sono e recomendar uma parada para descanso, ou se ele está com raiva e tomar alguma ação para evitar acidentes ou brigas de trânsito. Explicando um pouco melhor a portabilidade também do nosso sistema, ele teve o intuito de se tornar implementável para que outros sistemas consigam utilizá-lo com facilidade de ser implantado, dentro de outros projetos ou utilizar de forma individual mesmo, independente de outros sistemas. Sua portabilidade e ótima resposta, tanto em relação à velocidade como em relação à taxa de acerto, se deve ao fato de que foi desenvolvido na linguagem Python, que é atualmente a linguagem mais utilizada para desenvolvimento de softwares voltado para sistemas inteligentes, né? E, além disso, ela conta com fluidez e velocidade de resposta para atuar juntamente a outros sistemas, sendo que a IA abstrai tudo que está sendo feito internamente e retorna para o sistema predominante ou qualquer outra aplicação que a esteja utilizando somente a resposta da emoção predominante naquele momento. Então, por fim, obrigado a todos pela atenção. Eu quero agradecer aos órgãos que fomentaram essa pesquisa e serviram de base para que ela fosse realizada, né? Agradeço à FAPESB, ao Laboratório de Processamento de Imagem e Visão Computacional LAPVISC e à Universidade Estadual do Sudoeste da Bahia.
Okay, Tássio, thank you. Very nice work. Do we have any question from YouTube? Okay, so I'm curious about, do you implement this system and do you have some results about the reaction of the user using this system?
Não consegui entender, pode repetir, por favor?
Tássio, so I will speak in Portuguese. So, Tássio, estou curioso para saber se vocês já fizeram alguns experimentos com este sistema com diversos usuários e qual é a reação do usuário ao usar este tipo de sistema que reconhece emoções em lugar de ter uma pessoa real na frente.
Certo. Não fizemos testes ainda em campo aberto, né? Só com pessoas mesmo do laboratório. E a impressão que tem, às vezes, de uma certa violação da segurança e medo, né? Porque o fato de estar sendo analisado a todo momento e de que o sistema, na maioria das vezes, por possuir uma boa taxa de resposta, consegue acertar o que a pessoa estava sentindo naquele momento, causa uma certa agonia. Porém, a gente só fez esses testes em laboratório, por enquanto.
Okay. There is any question from YouTube? Okay, so thank you, Tarcio. So I will call the next presenter that I think that is Lucas Stewart-Nagel.
Hi.
Lucas, are you here?
Yes. Can you hear me?
So I will ask the authors please to present in English if possible.
Can you hear me? Hello.
Yes, Lucas?
Yes.
So Lucas, you are welcome. The next work is convolutional neural network with inception-like module for ball and goalpost detection in small humanoid soccer robot. So you are in control, Lucas, please.
Okay. I'm Lucas. I'm the main author of this paper, Convolutional Neural Network with Inception-like Module for Ball and Goalpost Detection in a Small Humanoid Soccer Robot. So, for the introduction, IT Androids is the Aeronautics Institute of Technology robotics team. It is a contestant in the RoboCup kid size category. Kid size robots have a human-like shape with height between 40 and 90 centimeters. They must be completely autonomous. IT Android's kid size robot is shown in figure 1. It complies with RoboCup rules, and since 2015, RoboCup rules determine a ball with at least 50% white color. This regulation has made our previous algorithms inefficient because they could not differentiate white objects properly. The main related works refer to other RoboCup contestants. It is worth noticing that 8 RoboCup teams still use an Intel CPU and rely on well-known machine learning frameworks, so they must adapt algorithms accordingly. The Murray et al. Adapts a region of interest selection algorithm to feed a CNN on a CPU. Their approach, however, struggles with blurred images. The situation is common as the robots walk, images from their camera are very often unclear. Cruz et al. Compares XNORNet and SqueezeNet fed with images from region proposals. They do so on a now robot with limited computer power. They achieve remarkable results, but they highlight that their algorithm needs to be retrained when robots change environment. So for our contribution, we preferred a fully convolutional approach to solve the problem because we believed it could generalize more cases, avoiding the increased work of training a neural network during a competition setup. We chose YOLO, the You-Only Look-Ons algorithm, to detect objects, since it works with a single CNN pass. We had to modify the algorithm to run on a computer with limited power that is running multiple tasks. During a RoboCup game, a single computer is responsible for movement, coordination, game strategy, decision-making, and localization. So we're going to talk about how we adapted the YOLO algorithm. YOLO is a complex algorithm to detect many objects. As our needs were simple, the algorithm could be simplified based on several assumptions. The first one is there is at most a single ball in the image, which is reasonable for a soccer game. There is at most one visible goalpost at a given time, as robots cannot see both goalposts during the game. They are located on opposite sides of the field. The robot seldom sees the complete goalpost because it is too high, so we track the goalpost's vertical supports. The goalpost supports are very similar. The only way to differentiate between them is when both are present in an image. About our architectures, we based our modifications of YOLO on the fast YOLO model, as it is designed for faster inferences. Our main changes were exchanging the two Philo fully connected layers for one fully connected layer implemented as a 1-by-1 convolution. The last layer of our CNN returns for each cell a 5-valued vector. Those values account for probability of an object's existence, the position, and its dimension. For more information on how we treat those variables, please read our paper. So, we stack those 5-valued vectors for each object we want to detect, the ball and the goalpost, and by doing so, we specialize our search for only two classes of objects. We iterate over the final CNN tensor to find the cell with the highest probability of containing a ball and the two cells with the highest probability of containing a goalpost. So about our YOLO implementation, we set the maximum execution time of our vision pipeline as 25 milliseconds because it is right below the average time between two image frames. We created two architectures to compare. The NNX has 8 layers and less filters in each layer than Fast YOLO, and Inception X adds an Inception-like module to NNX. This module is inspired by Google and Neto, for it improves detection with low increase in computational cost. We varied the number of filters in each layer to compare performance between architectures. Inception X is shown in this flowchart. It has two convolutional layers in parallel with one 3x3 convolutional layer that starts on the bifurcation after layer 5. So for our results, we see that only the image size of 160 and 120 was suitable for our time constraints and performed better on detection. We compared all the NNX with all the Inception X architectures and found out that NN3 and Inception 3, our most complex networks, had the overall best results. They both have pretty similar results on every metric, so we need to break the apparent tie. Inception 3 is slightly better on mean average precisions and classifications for goalpost detection, and we prioritize less false positives as they are harmful to the robot software, which has a ball tracker endowed by a common filter. If a false negative occurs, the filter is still able to propagate its estimate, but a false positive deviates the estimate towards a false ball. So we chose the Inception 3 to use in our robot. Now for the performance analysis. By analyzing the performance of our CNN, we saw false negatives with low object probability but correct bounding boxes when the ball was not fully contained in the image and on images with low luminosity. False positives were less frequent but appeared on luminous objects, white socks, and white objects outside the field. To mitigate those problems, we can add images from those cases on our training set, and we can use the field borderlines to filter objects outside the field. There is a correctly identified ball in this figure 3. The goalpost detection has low IOU scores, intersection over union, but high mean average precision. We do not think that those low IOUs will harm the robot software, as we only need the point of contact between the goalpost and the ground. 90% of our false positives occur outside the field, but they can be filtered using the borderlines. and blurry images cause the algorithm not to detect some goalpost supports. At figure 4, there's a correctly identified goalpost support. We sought to identify the best cost-benefit of classification performance and adjust the probability threshold correctly. We built a receiver operating characteristic curve, the ROC curve, to identify the probability that diminishes false positives while maintaining a high number of true positives. The probability threshold of 0.75, which is the red dot on this graph, is better than our empirical estimate of 0.3, the green dot. It decreases the false positive rate in 38% and the true positive rate in only 33.8%. But if we account for all objects, the results are less expressive, but we highlight that the goalpost detection is still secondary in this research. So, for our conclusions, by selecting the right parameters and architectures, it is possible to run a CNN on a limited environment. A convolutional neural network with 8 layers and an inception-like model has shown good performance and generalized many cases. Combined with Intel OpenVINO inference framework, we could run the vision pipeline in real time, faster than our camera's frame rate. For future works, we plan to decrease the number of false positives as they are harmful to our robot software, and we would like to deepen our research on goalpost detection and extend the algorithm to detect other objects on the soccer field. For acknowledgements, I would like to thank CNPq for the financial support to this research. We would like to thank our team sponsors for the made possible building a robot, and we are especially grateful to Intel for guiding us on using the OpenVINO framework. These are the references cited on this presentation.
Okay, thank you, Lucas. So, interesting work. I have a question about so I mean that you say that you have problem because both goals are similar. So you can detect what goalpost is if you have both in scene, okay, in the same image. Is it true?
Yes. Well, I mean, we track the goalpost supports, only their vertical supports. So when both of those supports are present in an image, we know that there is the right support and the left support. But we don't look for both goalposts, the complete object in the image, because goalposts are on the opposite side of the field. The robot cannot see them, both goalposts at the same time.
Okay, but did you think to use another kind of sensor or another information in order to fuse with the vision system to detect what if it is the right or the left goalpost?
We only know if it is the right one or the left one if we see both in an image, because we know their location. But if the system detects only one, we are unable to know which of them
I mean, for example, if you, in the last image, you recognize the right goalpost, for example, the next image is possible present the right goalpost too, okay? Did you use some kind of this information for determine if it is the right or the left post? Because I think that with a little increase in the complexity, you can detect the right post.
Right now, we do not differentiate the right from the left one, and we only track the the goalpost point of contact with the ground to help the robot localize itself in the field.
Okay. Are some questions from YouTube? Okay, I have one more question. Why you use YOLO? Is only real-time requirements, or is something more that you choose YOLO?
Well, first of all, we chose a fully convolutional approach because we wanted a system that would generalize more cases. We didn't want to go to a competition and keep retraining the network over and over again, because that consumes more time. And by using a fully convolutional approach, we don't need to run the CNN many times on an image. And that would be a problem if we did a region of interest selection.
Okay. Okay, thank you, Lucas. Thank you again. Nice work. So let's move to the next work. Okay. A comparison between 3 different parameterizations to represent planes for the mapping step of direct visual SLAM approaches. Who will present is Felipe Lins. Felipe, are you here?
I'm here, Professor Sina.
You are on control.
Okay, let me share my screen. Can you see my presentation? Professor, can you see my presentation?
Yeah, we can see.
It's okay.
Okay.
We can't see, we can't hear. You have to share computer audio. There is an option in Zoom, so you can go to Zoom controls, and okay. There should be 3 dots there, and there is an option to share computer audio.
And now, can you hear?
It's a bit slow. Please turn it.
Okay.
You can turn the volume up a bit more.
I did it. And now, it's better? Is it better?
Yes. I am hearing you now.
Okay, let's start again.
No, the video is too low. At least I can't hear it. Can you, Professor?
I'm not here now.
No?
Felipe, if you want, I can. Yeah, I have it. I can do it here.
Do you have my video?
Yes.
Yes, I do. Yes.
Okay.
Yes, we do.
It's a little different, but you can use it.
Okay.
A comparison of 3 different parameterizations to represent planes for the mapping step of direct visual SLAM approaches. This presentation is divided as follows. First, I'm going to introduce my work and present the motivation to write this paper. Second, some visual SLAM approach are going to be presented. After that, theoretical background and the three different parameterizations of the plane will be showed. Then, the adopted strategy of implementation is presented. And finally, in the result section, the performance comparison of the three parameterization of the plane will be showed. Then, I conclude this presentation. An important aspect of simultaneous localization map, or SLAM, arises from necessity to define descriptors of the environment. Most of SLAM approaches use geometric primitives to represent the environment, like points, lines, and planes. Many of these techniques use directing methods or old techniques based on optimization. An important information is given by Grisette that says that the choice of the parameterization may affect the optimization convergence speed. Therefore, the objective of this work is to compare the performance of three different plane representations in terms of image registration and efficient second-order minimization methods. In the last 10 years, many approaches of visual SLAM emerged with the popularization of RGBD sensors, providing large-scale map reconstruction. Many of these works used point or end planes to represent the environment. Here, we have three approaches that use planes. The first one used point and planes in the map reconstruction. They use 4 parameters to represent the plane. Already the second approach uses polar coordinate. Cass contested the use of these two parameterization. He said that the use of over-parameterized plane representation may result in convergence problems. Already, polar coordinates have singularities to represent the plane. Cass introduced a new plane parameterization that is minimal and does not suffer with singularity problems. Another area called direct SLAM emerged with the idea to estimate robot position and environment information through the direct matching of pixel intensity of 2 or more images. The general idea behind these techniques is a function that maps pixel position in an image to another. The parameters of this function represent the camera position change and parameters related to the environment. So, these parameters could be estimated by minimizing the photometric error. The work of Silveira is an example of direct SLAM that uses planes. He used 3 non-collinear distance from the camera to the plane. In this slide, we can see the function that maps a pixel in the reference image to another image. The parameter of this function, h, that is the homography, are the rotation matrix R, the translation vector T, and the normal unit vector N, representing the plane pi. The matrix K are the intrinsic parameters. As the interest of this work is to estimate only structured information, the position parameters are considered unknown. So, We can get the pixel position from one image to another by multiplying the age function with the pixel in the reference image. To find planes, we can formulate the problem as a nonlinear optimization problem, where the vector d represents the intensity difference between a set of pixels in the reference image and its corresponding in the other image. Applying the efficient second-order minimization, there is an optimization with high convergence rate, we can get this expression. The main advantage of this expression is that there is no need to compute second-order approximation. Now, the three different parameterizations used in this work are the components of the normal vector itself, the homogeneous representation of the plane, and the distance from the reference image to three non-collinear points belonging to the plane. Here we have the normal vector to plane that we call NVP. The parameters are the components of the N row. Now we can see the homogeneous plane representation, or HPR, and its relation with N row. Finally, we have the three non-collinear distance, or TND, and its relation with N row. About the implementation, to estimate planes in the environment, I used a ratified stereo image pair. The left image is the reference image, and it's divided in squares that we call regions. The optimization will search for plane descriptors for each region. Some of these regions are discarded due to the lack of texture, failure in optimization convergence, or deformation in 3D representation. Optimization techniques generally need an initial estimate of the parameter to be optimized. Therefore, a disparate map is used to generate initial estimates of each region. Here we can see in the upper left side the reference image. In the right side of the left image, we can see the red regions of each parametric models that represents the successful planes estimated. The blue regions are discarded regions due to low texture, and the lower images present the ground truth and the 3D representation of the regions. In the result section, to compare the three planes parameterization, 5 types of scene from the Middlebury data set were adopted. 3 metrics were used to compare parameterization performance. The first one is the number of successful optimized regions in the image. the second one, the percentage error of the normal vector estimated with relation to the normal vector of the crown tooth. Finally, the last metric adopted was the number of steps until the optimization converges. Now we can see the results in this horizontal bar chart. First, we can see that the homogeneous plane representation and the 3 non-collinear distance achieved almost 15% of all regions available in the image. On the other hand, the normal vector to the plane achieved less than 10%. In the percentage error, a similar result of the 3 model was achieved. Finally, with the relation of the number of interactions, the 3 non-collinear distance converged 3 times faster than the homogeneous plane representation, and 4 times faster than normal vector to plane. To conclude, we have shown that the 3 non-collinear distance parameterization found more planar regions and converged faster than the other parameterizations. Thanks for your attention.
Okay, thank you, Felipe. Thank you for your presentation, nice presentation. So I will call, there is any question from YouTube now? Okay, I have one question. You say that you said this parameterization only in the mapping step. And what about using this parameterization in the localization step of the SLAM process? There is any additional problem, or do you think that it's straightforward to use these parameterizations? And which one do you think that will behave better?
As we can see in the result, the 3 non-collinear distance showed to be more faster than the others parameterization. So as this paper is part of my work, I'm developing a SLAM technique, and I use it. I thought that this information about the comparison of the 3 I tested more than 3 parameterizations. So the main parameterization that I saw in my research, and I saw these 3 parameterization. So as this is part of my work, and I think that the 3 non-collinear distance is better, and I tested with in the SLAM, because it's only part where I said, and the 3 non-collinear distance appeared to be more faster than the others. I don't know if I answer your question.
Okay. Okay, thank you, Felipe. There is any more question from YouTube? No? Okay. Before moving to the next paper, Professor Luis Marcos asked me to announce that the CIR meeting that will be happening today, it was canceled, and will be back tomorrow with Professor Marcelo Becker plenary, okay, at 9 a.m. So let's move to the next paper, a comparative evaluation of learned feature descriptors on the hybrid monocular visual SLAM methods. Who will present is Hudson Bruno, I think. Hudson, are you here?
Hi, I'm here. Can you hear me?
Yes, yes. You're welcome.
Thank
you.
you.
You are in control. Please, you can do your presentation.
Let me just share. Hi, my name is Hudson, and I will talk about our paper that is called A Comparative Evaluation of Learned Feature Descriptors on Hybrid Monocular Visual SLAM Methods. This work was made with Professor Esther Colombini in Institute of Computing Unicamp. First, I'll start with a brief introduction. The visual odometry is an algorithm that estimates the camera position and orientation based only on the images from the camera. And the visual SLAM is the algorithm that uses the odometry to estimate the position, and additionally it creates a 3D model of the environment. This pipeline shows the basic steps of a traditional visual SLAM algorithm. It is composed of a tracking step, a mapping step. In tracking, we extract features and estimate motion. In mapping, we represent the map and perform some local optimization. And if we detect some loop, we can call a global optimization method that will correct the global trajectory. And if we are lost on the environment, we can apply the relocalization module that will look for a place that we already visited before and perform the relocalization. However, the traditional algorithms have some drawbacks. One of them is when we are in challenging environments, for example, in bad illumination or ill exposure environments, or when the camera is at a high speed, then we can have some motion blur that will affect our algorithms. Therefore, we can use the deep learning-based algorithms that have been used recently to create more robust algorithms that are robust to this challenging situation. There are two groups of deep learning-based methods: the end-to-end methods, that are the methods that replaces the entire visual odometry pipeline with a deep neural network. And there are the hybrid methods. These hybrid methods will replace only few modules of the pipeline with a deep neural network. Recently, some work proposed detecting and describing and the local features on the image with deep neural networks. For example, Lift, LFNet, and Superpoint are some of these networks. However, a comparative evaluation of these descriptors in hybrid visual SLAM pipelines was still not presented in the literature. So, our contributions are: first, a hybrid monocular visual SLAM pipeline that will adopt here to extract the features of deep neural network and perform the rest of the pipeline with a traditional method based on OrbSLAM. And the second contribution is an approach that we created to evaluate the robustness of the hybrid visual SLAM algorithms based on two datasets, Kitty and NeuroMath, with the application of some camera distortions in some scenarios. The Kitty dataset is a set of images recorded from a moving car in a city, and the Euroc dataset is another set of images recorded from a drone that is flying around a room. And the distortions we created are the underexposure that we emulated with gamma power transformation and the overexposure. With these cases, we can evaluate the robustness of our algorithms. Now I will show the methodology we applied in this work. We chose two feature descriptors to perform our evaluation. The first one was lift. That is, its pipeline is shown here. Lift was trained in a supervised way. The ground truths are obtained from a structure from motion algorithm that uses shift features. But this network takes 36 seconds to generate the descriptors from an image from Kitty dataset and 35 seconds for an image from Euroc. This estimation is in my computer, that is a GTX 1050 Ti GPU. And the LFNet, as we show the pipeline here, is a self-supervised network. It exploits depth and relative camera poses from the images to train the network. And it's much faster. It takes 0.35 seconds to generate the descriptors for Kitty and 0.31 seconds for Euroc dataset, also in my computer. And the traditional visual Islam pipeline we adopted here, as I said earlier, is based on OrbSLAM, and it has three main steps here. The tracking step that performs the feature matching, then predicts the pose and optimizes it. The mapping step that builds a co-visibility graph based on OrbSLAM and creates map points. And the loop closure step that runs in parallel and relocalization step. They all use a similar system where we created a visual vocabulary for each descriptor with the two-mono VO dataset that it has outdoor and indoor images. And we also created a bag of words for each of the keyframes and compute the similarity between keyframes in order to detect if a place is being revisited. If it is being revisited, we create the loop closure and perform the global optimization. And we can also detect if we were lost, if we are in the place again, and relocalize ourselves. Now I will show you my results. These are the results on the Kitty dataset from all algorithms. We can notice that the deep learning based algorithms perform better than OrbSLAM algorithm. In bold here, we have the smaller error, and in underline the second smaller one. So we can see that LeftSLAM was the algorithm that performed better in most of the cases. We can also see here in the qualitative results that in sequence 0, OrbSLAM was the only algorithm that was never lost during the trajectory. We can see when an algorithm is lost by these straight lines that connects the point where it was lost and where it was relocalized. But in sequence 03, we can notice that OrbSLAM performed worse than the other algorithms that are much closer to the ground truth here. So we notice that our algorithms are much better in smaller sequences. In Kitty 06, we can see that Oxlam was the only one that couldn't find a loop closure here, and the other algorithms could find it and optimize the poles. And in sequence 07, only LiftSlam could find the loop closure, and the other algorithms couldn't. And here we have the quantitative results on the EROC dataset. We can notice that LFNetSlam was either the best or the second best in all sequences, while LiftSlam was never the best algorithm in these sequences. We can notice by the qualitative results that most of the algorithms were kind of similar in MH01 and MH02 sequences, but in MH04, for example, LiftSlam was much worse than the others and has a huge error accumulated here. And these are the results of the robustness tests we performed. And we can see that OrbSlam could not finish tracking in all sequence with gamma bigger than 1. That means underexposed scenarios, while Lift and LFNetSlam wasn't able to perform the tracking on sequence with gamma equals to 4. However, they could perform the odometry on the others. And we can notice in some cases where the algorithm actually improved their performances on scenarios with distortion. And this might happen because the distortion are actually in some cases helping us to select the best features for our algorithms. And these are the results of the robustness test. We can notice that LiftSlam was not affected by the distortions. The LFNetSlam was affected in some sequence, as well as OrbSlam. And now our conclusions. We concluded that the algorithms with learned features could improve the accuracy of OrbSlam in most of Kitty and UROC sequences, and also LiftSlam presented a better performance of the odometry in outdoor environments, while LFNet presented a better performance in indoor environments. And we can notice also that the deep learning-based algorithms were more robust to camera U exposure conditions than OrbSlam. And as future, we plan to perform feature selection with an attention-based mechanism, and this will help us improve our accuracy as we have seen in the noise tests. We also plan to fine-tune the neural networks with VO sequences in order to improve the robustness and the accuracy of the feature structures, as we have already shown in another work that this fine-tuning can improve the accuracy of the deep learning-based algorithms. These are our references, and we'd like to thank CNPq, CAPES, and Quinto Andar for supporting this project. Thank you. Hi,
Thank you, Hudson. There is any question from YouTube? No? Okay. I was curious about something that you said, that LFNet performs more fast than Lift in your computer, okay? But in indoor environments, LF performs better than Lift. What do you think that is? Why is this difference that performs faster and better?
Yeah, LFNet was faster to extract the features, okay, and performed better in indoor, but Lift was better in outdoor environments. That was from the Kitty sequences. So although Lift wasn't faster and not better in indoor environments, it still had some good performance in outdoor environments.
But why do you think that this happened?
Okay, I think that this happens because the way they train the networks and the data sets they used. That's why we plan to fine-tune the networks with VO sequences, as we did already with Lyft, and we see that the performance of the network improves. So we plan to do it with LFNet and compare again with this fine-tuning.
Okay, thank you. There is any more question? No? Okay, thank you, Hudson.
Thank you.
For the nice presentation. Okay, so the session is ending, and I will thanks all the authors by the interesting papers. So I will pass to the next section now.
Thank you, Professor. Professor Adnan is starting o concurso de teses e dissertações, isn't it? He told me that's going to be in Portuguese, so the audience should be a little bit more comfortable. And please, Professor Adnan, you could start when you are ready.
Oi, pessoal, boa tarde a todos. A gente vai dar início agora à sessão do workshop de teses e dissertações, certo? Só para a gente dar um início a essa sessão, o workshop de teses e dissertações ele tem o propósito, né, de possibilitar trocas de ideias para que os estudantes tenham dicas e possam aprimorar seus trabalhos que estão em andamento, que estão em desenvolvimento, certo? Então, a gente, com o workshop de teses e dissertações, a gente promove aí o intercâmbio de conhecimento entre os participantes. Então, é uma boa oportunidade para que aqueles que estão desenvolvendo seus trabalhos possam apresentar e ter algum feedback, né? Nesse ano de pandemia, a gente está organizando o workshop de teses e dissertações, o professor Reinaldo Bianchi, da FEI, e eu, professor Anderson Abner, da Universidade do Estado do Rio Grande do Norte. Estamos organizando, estamos à frente do workshop de teses e dissertações, e também do concurso de teses e dissertações em robótica, né? E nós queremos agradecer ao pessoal da organização do LARS, que está nos ajudando bastante. Agradecemos ao professor Luiz Marcos pelo convite e pela confiança de nos colocar como chair e como organizadores do WTDR. Agradecemos também ao professor Júlio Melo, que está à frente da parte técnica operacional do LARS, do WTDR e do WRE, ao professor Bruno, que também faz parte da organização do LARS, ao professor Paulo Drius também, que está na organização do LARS, e toda a equipe que está ajudando na organização desse evento virtual. Queremos agradecer grandemente a vocês, certo? Nessa sessão do workshop de teses e dissertações, nós temos 3 trabalhos a serem apresentados. O primeiro trabalho é Comparison Between Meta-Heuristic Algorithms for Path Planning, da Lídia Rocha. A Lídia já está por aqui, não é isso, Lídia?
Tô sim.
Pronto, a Lídia já está por aqui. Temos também o trabalho EEG, Signal Detection and Analysis with Application in Educational Robotics, do Adam Pinto, que é da USP, juntamente com a professora Roseli, da USP. E o terceiro trabalho, Automated Behavioral Box for Tactile Discrimination Test, do José Wanderson, da UFRN, que é orientado pelo professor Luiz Marcos, certo? Então, vamos iniciar com a Lídia. Pode apresentar o seu trabalho, Lídia. Fique à vontade. Você tem 20 minutos, incluindo as perguntas.
Certo. Vou compartilhar a tela aqui com o vídeo, tá bom?
Ok.
Tá vendo aí?
Sim, estamos vendo.
Tá tentando compartilhar o áudio, Lídia. Não sei se coloca para compartilhar o áudio. Tem uma opção aí no Zoom. Procurando.
Ah, tá, beleza. Pensei que já tava...
Foi? Simulation.
Foi sim.
Tá, vou voltar então. Desculpa.
Hello everyone. I will present the paper Comparison between Materialistic Algorithms for Path Planning developed by me, Lídia Rocha, and Professor Dr. Kellen Valdini at Federal University of São Carlos. I will present the introduction, methodology, simulation and analysis, conclusion, and reference of this work. UAVs are being adopted in several areas, as surveillance, construction, environmental monitoring, and others. Over the years, they have become more autonomous, generating your own path and carry out the missions. Path planning is an essential area of robotics that aims to find a path for the robot to move from the starting node to the goal. Also, UAVs have some restrictions, so the path should respect them. To minimize UAV movement problems, paths may be formed from smooth curves. Nowadays, the complexity of missions and environments has grown exponentially, such as jungles, mountains, labyrinths, delivery, and others. Some of the problems even have complexity non-deterministic polynomial time. Materialistics don't have complex mathematical knowledge about the behavior, so they can be better to solve those problems. The importance of materialistic methods comes from optimal results, not necessarily the best, but in a variable time, so it is widely used for optimization. Materialistic algorithms are one of the best techniques to optimize problems with NP hardness. Some authors have developed studies about materialistic algorithms, as Shaw, Twarwat, Koch, and Krell with particle swarm optimization, G, Panda, and Dewang with Grey Wolf optimization, and Lu, Panda, and Go with Glow Wars sword optimization. In these works, the algorithms are improved to carry out a mission, sometimes doing a fast comparison between some algorithms. In this work, we choose the main three materialistic algorithms used in literature to analyze your complexity according to different environments and do a comparative analysis of them in 2D environments, considering metrics as average, variance, and standard deviation applied to the execution time and path length. The path generated needs to be smoothed for follow UAV restrictions. We used cubic spline interpolation to smooth them, being better for the robot to move and make curves. The splines consist of dividing the range of thrust into subintervals and interpolating based on cubic polynomials. The cost function is defined by equation 2, where k is the coefficient to avoid obstacles, L is path length based on Euclidean distance, len is the distance between UAV and each obstacle, Rho is the radius of obstacles. With this cost, the penalty for collision is bigger, decreasing the chance of collision on the path. Particle sort optimization is based on the movement of a bird flock. The best simulation demonstrates that the movement is based on the speed of the nearest neighbor and randomness. That is the use of the algorithm, where the velocity is defined by equation 3. To define the velocity, is considered the values of the nearest neighbor and randomness. O is the similarity with the last velocity. Grey wolf optimization is inspired by the hunting process found in grey wolves. They follow a social hierarchy where alpha, beta, and delta have the best positions, respectively. In the grey wolf algorithm, alpha wolves represent the best solution, followed by beta and delta, and that is the
use the algorithm where the best position is defined with equation 5. Glow wars swarm optimization is developed based on the behavior of glow wars. The glow wars can change the intensity of the bioluminescence. Each glow war has a luminous pigment called luciferin, which is modified according to its position, allowing the glow war to shine at an intensity similar to that of the function being optimized. Each glowworm chooses the neighbor with the highest luciferin using a probabilistic mechanism and moves towards it. However, the glowworm can only follow a certain number of wars nearby and have a limited distance. Naturally, glowworms use your bioluminescence light to signal in direction for other wars. There is the used equations in the algorithm. We studied each algorithm to define the complexity. The time complexity of each algorithm is based on a number of obstacles in environments. Particle swarm optimization and gray wolf optimization have time complexity as BO, number of iterations times size of population times number of obstacles plus size of population. And glow war swarm optimization has big O, number of iterations, size of population, between parentheses, size of population, number of possible neighbors, and number of obstacles, plus size of population, because it's necessary to update the range tension between the glow walls and check if all neighbors, which will be the best to follow. So, glow war swarm optimization tends to be slower than others. The used parameters for each algorithm can be seen in this table. Each algorithm had a population of 15 elements with 50 interactions and was performed 100 times to determine the variance and standard deviation of algorithms for execution time and path length. The simulations are made in two scenarios, with 100 meters of area and 6 obstacles, and the other with 900 meters of area and 11 obstacles. In this figure, it shows the trajectories generated to unstructured environments with 10 and 30 meters in each side, respectively. As we can observe, the path generated by each algorithm have been smoothed with the splines to facilitate the mobility of UAVs due to limited dynamics and the aerodynamics. In this table can be seen the metrics applied to path length and time to generate the path. Gray wolf optimization can find the path in less time, with low variance and standard deviation from time, which shows reliability in its execution time. However, particle swarm optimization managed to find the shortest path, also having low variance and with a small standard deviation, showing reliability in the results found. According to your complexity analysis, the glow war swarm optimization has a higher time complexity, which can be determined by analyzing the average time between the two algorithms. Despite the particle swarm optimization doesn't obtain the shortest time, the algorithm can be considered as the one with the best performance because it obtains the shortest path length and similar time to gray wolf optimization, which obtains the shortest time. Also demonstrates the smallest variance and standard deviation concerning the path length and execution time. Thus, the results are to environments with 10 meters. With 30 meters, the results are similar, except the variance and standard deviation of distance that are very variable. In environments with 30 meters, the minor variance and standard deviation were of gray wolf optimization shortly thereafter of particle swarm optimization. That is, when the environments increase, the particle swarm optimization becomes less reliable and the glow war swarm optimization maintains the same reliability concerning find the best path. According to this table, the algorithms have a small difference when the size of environment is changed in relation to average path length and execution time. Thus, in small environments, the particle swarm optimization proved to be better for using problems that demand reliability and need to operate in real time. However, in large environments, the glow war swarm optimization would be a better choice. which despite presenting a longer path, is still fast and more reliable. Where made the comparison between particle swarm optimization, gray wolf optimization, and GLOW-WAR swarm optimization according to the metrics for execution time and path length for understand what's the better algorithm for each task. The GLOW-WAR swarm optimization presents a longer execution time, which was already expected due to its high time complexity. Gray wolf optimization shows the best execution time among the algorithms, while particle swarm optimization returned the shortest path between them. In small environments, particle swarm optimization has a low standard deviation and variance in execution time and path length, being better to perform real-time tasks. But in large environments, the gray wolf optimization is the best option according to its reliability. For future work, will be realized a study to prove how is the best size of population and number of interactions to result in the best results to these algorithms. Besides, to use in three-dimensional, dynamic, and unknown scenarios. And we will add a security area to turn the trajectory more secure and feasible to the UAV carryouts. Those are the usage references. Thanks for listening.
Ok, esse foi o trabalho de Lídia. Parabéns, Lídia. E queríamos saber se há alguma pergunta dos participantes, do pessoal do YouTube. Nenhuma? Lídia, eu tenho uma pergunta aqui. Você já conseguiu aplicar os seus algoritmos em um robô real? A gente sabe que simulação tem todo um ambiente que favorece, né?
Sim, sim.
Mas quando a gente aplica nos robôs reais, a gente tem algumas características a mais aí para lidar.
Certo.
Queria saber se você já aplicou em robôs reais e o que aconteceu.
A gente ainda não fez o teste para robôs reais, mas o algoritmo ele funciona em paralelo. Por exemplo, ele vai gerar o algoritmo e ele consegue passar a trajetória por ROS. Então, ele consegue... Vai ser independente... Calma. Deixa eu tentar explicar melhor. Calma. A trajetória gerada, eu não coloquei fotinho aqui, mas ela condiz com o que um drone consegue se movimentar. Ou seja, todos os movimentos dele são sinuosos, são bem suaves para ele não ter problema no controle. E esse algoritmo em si, ele vai retornar a posição x e y dessa rota, ele não está retornando z. Desse modo, eu posso chamar no start do drone, para ele gerar a rota e eu faço apenas ele seguir. Então não seria um grande problema, já que ele está considerando que precisa ser sinuoso, precisa desviar com tanta distância do obstáculo e tal. Não sei se responde a pergunta.
Sim. Tudo bem. Alguma outra pergunta? No YouTube. Ok, sem mais perguntas. Obrigado, Lídia. Parabéns novamente pelo trabalho.
Obrigado. Até mais.
Até mais. Agora a gente vai para o segundo trabalho. Tem o título de EEG, Signal Detection and Analysis with Application in Educational Robotics, do Adam Pinto. O Adam entrou em contato comigo e já avisou que não seria possível apresentar o trabalho, porque ele está como chair de uma das categorias lá da competição. Então, eu pedi para o pessoal da técnica para dar o play no vídeo do Adam.
Ok, Adam, só um segundo.
Olá, meu nome é Adam e eu vou apresentar o meu trabalho, Detecção e Análise de Sinais EEG com aplicações em Robótica Educacional, que foi feito Instituto de Ciências Matemáticas de Computação, ICMC-USP, com orientação da professora Roseli Romero. Esse é meu outline. Eu vou falar uma introdução, fundamentação teórica, experimentos, resultados e conclusão. Bom, meu trabalho se inclui dentro da parte de HRI, que é a interação homem-robô, porque ela entende e molda a interação entre os seres humanos e os robôs. Boa parte do aceite que os humanos têm em qualquer tipo de atividade, né, com algum dispositivo ou com robô depende dessa forma como a interação acontece. Então a gente tem um trade-off entre a quantidade de informação e o tempo de processamento, para que a interação seja o mais natural possível. Quando
Pessoal, vocês me escutam?
Sim, mas o vídeo travou.
Acho que o vídeo travou, né?
Aham.
Júlio? Júlio, você me ouve?
Parece que ele não está ouvindo.
Abner, você consegue dar um play no vídeo? É porque ontem a gente verificou que quando eu dou play no vídeo, o vídeo sai um pouco com algumas interferências. Eu acho que é algum problema do Zoom no Linux.
Eu vou tentar dar um play aqui no meu computador. Um segundo.
Beleza.
RI, que é a interação homem-robô, porque ela entende e molda a interação entre os seres humanos e os robôs. Boa parte do aceite que os humanos têm em qualquer tipo de atividade, né, com algum dispositivo ou com robô depende dessa forma como a interação acontece. Então a gente tem um trade-off.
Vocês estão vendo a apresentação?
Sim, Júlio, dá para ver e dá para ouvir bem.
Isso.
Entre a quantidade de informação e o tempo de processamento, para que a interação seja o mais natural possível. Quando aplicada à educação, a HRI ajuda no relacionamento do aluno com o dispositivo que está ensinando ele. E a gente sabe que os robôs eles podem trazer um efeito de novidade e influenciar o sistema, ou seja, durante o momento ele é muito interessante e aí, de repente, ele se torna muito repetitivo tal, e esse interesse decai de uma forma muito rápida. Para evitar ou para tentar driblar esses problemas, a gente usa as Brain Computer Interfaces. Elas são uma forma diferente de se obter informações, ou seja, a gente obtém informação diretamente do cérebro e não de algum outro sensor, como câmera, por exemplo. E ela pode ser classificada de 3 formas: invasiva, não invasiva e semi-invasiva, dependendo se existe ou não a necessidade de alguma cirurgia. Por não ter a necessidade de cirurgia, a não invasiva é a mais comum, e dentro da não invasiva, uma das mais utilizadas é a eletroencefalografia. Essa técnica consiste em posicionar os eletrodos no escalpo, ou seja, bem longe do neurônio em si, né, para poder obter informação a partir do DDP, que é a diferença de potencial. Esse sinal acaba sendo muito ruidoso e cheio de artefatos, porque ele está muito longe do neurônio em si, e ele pega mudança de batimento de coração, piscar de olhos e outras informações. Porém, a gente sabe que existem alguns padrões de atividades cerebrais que são associados a algumas atividades específicas. E para entender esse padrão foi criado um posicionamento de eletrodos, que é o sistema 1020, que a partir desse sistema a gente consegue entender o que está acontecendo dentro do cérebro de acordo com qual quantidade de neurônio, né, com qual grupo de neurônio que está sendo ativado. A gente também sabe por pesquisas anteriores que pequenas diferenças no posicionamento eles influenciam no resultado das análises. Dentre esses potenciais, um deles é o ERP, que é o Error Related Potential. O potencial evocado, ou seja, ele acontece a partir do momento que a pessoa recebe algum tipo de estímulo, e ele é considerado um termo guarda-chuva, porque ele engloba vários tipos de sinal que podem ser medidos considerando a resposta ao erro. O que a gente viu com relação aos trabalhos em BCI é que boa parte dos trabalhos foca em potenciais bem conhecidos como o Oddball ou P300 e também focam muito em aplicações para a área médica, para neurofeedback e também para a imagética motora, deixando a educação um pouquinho de fora. Aí a gente tem uma imagem de dois tipos de erros, eles têm mais ou menos a mesma cara, mas eles têm algumas diferenças. O nosso objetivo, então, é usar filtragens não convencionais para aplicação de PCI na educação e comparar os resultados de acurácia utilizando também Deep Learning e algumas outras técnicas clássicas. Essa é uma arquitetura do nosso sistema, a gente pegou algumas bases da literatura que utilizam capacetes comerciais, fizemos um jogo e propomos uma aplicação com um capacete melhor, com um capacete médico, e também algumas aplicações com robô. Colocamos tudo isso numa base de dados, fizemos a filtragem e classificação para saber se existia ou não a existência do ERRP. A gente distribuiu os eletrodos utilizando o capacete VAMP, da forma como é mais comum na literatura, mas a gente só usa o FZ e o CZ, que são os mais relacionados ao Error Related Potential. A gente teve várias amostras, porém pequenos detalhes acabavam estragando esses testes, alguém que batia na porta, ou o estado mental da pessoa não era bom no momento, o que fez com que apenas 8 indivíduos saudáveis fossem escolhidos para essa base de dados que a gente disponibiliza para ser utilizada. Todos os participantes foram voluntários, não sabiam os propósitos dos experimentos e tinham mais ou menos o mesmo nível de educação e conhecimento, tanto sobre robótica quanto sobre sinais biomédicos. Nós definimos então um jogo, né, que era usado para provocar ERP. Então ele é um jogo parecido com Pac-Man, você só precisava buscar o cérebro, e ele a princípio é um jogo bastante fácil, as pessoas não teriam dificuldades para poder executá-lo. Em uma imagem do jogo, ele não tem nenhum tipo de outro obstáculo, fazendo que as pessoas imaginassem que fosse um jogo fácil. Então a gente tinha uma etapa de calibração em que não acontecia nenhum tipo de problema, a pessoa tinha alguns segundos para pegar os cérebros que ia contando a sua pontuação, e depois dessa etapa a gente ia para o jogo real. No jogo real existiam alguns erros forçados, ou seja, as pessoas não sabiam que isso ia acontecer, mas aconteciam alguns tipos de erros. O zumbi ficava parado, ou ele agia mais lento, ou agia ao contrário do que a pessoa pedia, para que a gente tivesse a incidência do RR sabendo do erro. E depois disso, a gente também fez uma interação com o robô. O robô se apresentava, tentava ser o mais simpático possível, porém ele precisou ficar parado, porque a gente percebeu que a movimentação dele causava muito ruído no EEG, e aí ele fazia um quiz sobre sinais biomédicos e programação de computadores, ou seja, fazia perguntas fáceis para as pessoas que estavam participando, já que conheciam bastante de sinais, e difíceis, já que eles não tinham tanto conhecimento assim de programação, de coisas mais específicas de inteligência artificial. E ele exibia 3 tipos de comportamentos durante esse trabalho. Ele agia da forma esperada, quando a pessoa estava certa, ele falava que estava certo, quando estava errado, ele falava que estava errado. Ele agia ao contrário, ou seja, quando a pessoa estava certa, ele falava que estava errado e vice-versa, ou ele se confundia entendendo uma outra coisa. Obviamente, isso era um comportamento programado. Então, a gente primeiro o EOG, que era uma informação a mais para poder fazer a remoção dos artefatos. Nós seguimos o que é mais comum da literatura, a filtragem do sinal, os momentos da ERP eram bem definidos e os primeiros resultados foram bem insatisfatórios por conta da janela que nós utilizamos. Nós fizemos uma nova amostragem com as janelas bem fechadas, onde acontecia exatamente o erro em alguns outros pontos, o que era considerado normal, e aí a gente teve um resultado satisfatório. Os resultados da MLP são bem próximos ao que se é esperado na literatura, e a gente teve a CNN tendo resultados melhores, já nesse contexto das bases da literatura. Depois nós pegamos os nossos trabalhos e tivemos que fazer um pré-processamento, afinal de contas o sinal vinha todo ruidoso e sem esse tratamento anterior. E aí a gente tem uma média dos RPs que a gente tinha, então é possível perceber que era realmente bastante ruidoso. E a gente fez comparações de acurácia na base criada, já tendo uma demonstração de uma melhora muito grande quando utiliza a CNN. A MLP se manteve mais ou menos dentro do padrão, um pouco melhor, e a CNN já foi bastante melhor nesse caso. A gente resolveu aplicar mais uma família da Wavelet, a da UBX, tendo o resultado ainda melhor, chegando até a 96% de acurácia. E a gente entende que isso aconteceu por um maior controle da informação, eu sabia exatamente onde estava cada um dos momentos de erro. Isso ajudou bastante a ter essas melhorias pequenas na MLP e principalmente na CNN, porque quando eu dividia o sinal, decompunha o sinal nas wavelets, eu sabia onde estavam as informações temporal e a CNN usou isso para classificar de uma forma muito melhor, obtendo os resultados que nós tivemos. As transformadas wavelets elas foram melhor praticamente em todos os testes. Pensando nisso, com esse resultado do capacete, nós voltamos a um capacete mais comum, que é o OpenPCI, para fazer novos
seu
testes
áudio
com
ele
alunos.
cortou aí.
Nesse caso foram feitos com crianças e a gente percebeu que teve uma queda bem grande.
Vocês me escutam ainda?
Sim. Sim, Abner. Sim.
Eu tava vendo o vídeo.
Só o vídeo.
Ah.
Tentar voltar e colocar novamente.
Comum, que é o OpenPCI, para fazer novos testes com alunos. Nesse caso foram feitos com crianças e a gente percebeu que teve uma queda bem grande do resultado, ou seja, o resultado ficou muito pior. Crianças são mais inquietas e o sinal também era bem ruim. 8 crianças participaram, novamente mais crianças acabavam participando, mas as suas informações foram descartadas e o teste indicou uma grande sensibilidade ao hardware utilizado, que a diferença entre os tipos de eletrodo seco molhado, a análise de impedância que não é feita nesses outros capacetes, tudo isso acabou sendo bem impactante para o resultado final. A gente não conseguiu reproduzir os testes que nós tivemos com o capacete VAMP. E foram feitos testes com um outro capacete, que é o Neurosoft, mas também foram descartados porque o sinal estava bem ruim. Aqui uma pequena demonstração do que foi obtido pelo OpenPCI, é perceptível que também é um sinal bastante ruidoso. E aí a gente vai para os resultados com os robôs. Os resultados dependiam muito das pessoas realizarem a tarefa solicitada, entenderem muito bem o comando do robô, que não acontecia sempre. Elas tinham que apertar um botão caso soubessem a base de dados acabou ficando muito pequena, porque as pessoas se confundiam na hora de apertar os botões, mas o que a gente conseguiu perceber, que quando o aluno sabe a resposta, os comportamentos 2 e 3, eles mostram uma variação no tipo de RP, ele tem uma pequena variação de intensidade, e quando ela não sabe a resposta, emerge um outro padrão. A gente tem aqui uma demonstração, a parte de cima é um RP um pouco mais clássico, a parte de baixo a gente vê um padrão um pouco diferenciado, em momentos em que ela sabia a resposta e não sabia a resposta. Para o padrão de RP, a nossa rede continuou acertando por volta de 80% na média, o que está dentro do esperado, porém nesse outro padrão ele caiu para 60%, 60 e poucos por cento, o que mostra que ela não conseguiu generalizar para essa situação específica, é um erro bastante diferente do que era esperado, ou seja, quando você não sabe a resposta, você emerge um outro tipo de padrão. Nossa conclusão é que os resultados mostram a importância da filtragem, do pré-processamento do sinal, que permite, então, melhor acurácia. A gente precisou selecionar manualmente boa parte dos testes, o que não é indicado, mas ele ainda assim foi comparado com a literatura e foi muito bem quando dentro da nossa própria base. A extração de características é extremamente importante para processos de PCI. A gente encontra tem pouquíssima influência no resultado final, porque às vezes a gente tem uma wavelet bastante mais complicada para ser calculada, acaba fazendo com que o robô tenha uma demora muito maior para a resposta e ele não tenha um ganho significativo. Então é melhor usar uma família como a RAR, que é uma família bem simples de wavelet, que conseguiu um resultado bacana. E a CNN também se mostrou bem superior à MLP, muito pela característica temporal. A gente sabe das limitações do trabalho, ele é muito sensível ao rádio, tem poucos extratores comparados, seleção manual das janelas, as dificuldades do headset e também a dificuldade de aprovação por conta do comitê de ética, que foi uma dificuldade para o nosso trabalho. E como os trabalhos futuros, nós queremos fazer comparação com outros extratores, com outros classificadores, teste de viabilidade do módulo com todo o sistema e mais testes para definir o momento do erro durante as atividades e entender esse outro sistema, esse outro erro que apareceu no sistema. É isso, muito obrigado.
Bom, pessoal, vocês me ouvem?
Sim.
Yep.
Ótimo. Então, esse é o contato do Adam. Quem tiver alguma dúvida a respeito do trabalho dele, só enviar um e-mail para ele, entrar em contato, que com certeza ele irá responder. Né? Agora vamos para o último trabalho, que é o trabalho intitulado Automated Behavioral Box for Tactile Discrimination Task, do José Wanderson, orientado pelo professor Luiz Marcos. O Wanderson está por aqui?
Todos me ouvem aí?
Sim.
Sim, Wanderson.
Pode compartilhar sua tela.
Aqui. Eita, esqueci aqui uma coisa. Conseguem ouvir meu áudio?
Sim.
Sim.
Bom, meu trabalho está intitulado como Automated Behavioral Box for Tactile Discrimination Task, que é a automatização de uma caixa comportamental para a tarefa de discriminação tátil. Me chamo José Wanderson Oliveira Silva, sou doutorando do curso de Engenharia Elétrica da UFRN, junto com o professor, meu orientador, o professor Luiz Marcos. Dentro desse estudo, nós trazemos os roedores, que são um modelo animal muito utilizado para esse tipo de experimento. Ele tem várias vantagens dentro das citadas. Uma delas é desde o seu tamanho, ciclo reprodutivo e o seu manuseio. São itens bastante importantes para se aderir a esses tipos de animais, para esse tipo de treinamento. Dentro desse contexto, para se trabalhar com esses animais, nós inserimos um elemento chamado condicionamento operante. O condicionamento operante é um método onde a gente insere uma aprendizagem nova, de forma que essa aprendizagem ela é baseada na utilização de estímulos. Esses estímulos, desde auditivo, tátil, degustativo, certo? E dentro desses estímulos, eles vêm também, eles recebem uma consequência devido ao seu treino. Essa consequência do ambiente pode ser um reforço, uma punição, e tudo isso tem como função criar, certo, uma nova resposta. Então, buscamos, dentro desse tratamento, buscar uma resposta para um dado problema. Dentro disso, nós temos vários tipos de caixas comportamentais operantes, que nós denominamos classe CCO. Dentre elas, temos o labirinto em Y e o labirinto em T. O labirinto em T, ele é muito utilizado para teste de ansiedade, que permite avaliar o animal com respostas relacionadas a dois tipos diferentes de ansiedade, desde o transtorno de ansiedade generalizado, quanto o transtorno de pânico. Então, esses modelos são aplicados para essa forma específica. Dentro desse mesmo ponto, nós temos a caixa comportamental desenvolvida há muito tempo por Krupa. Essa caixa aqui bem complexa e bem cheia de recursos eletrônicos. Essa caixa ela é utilizada também para a tarefa de discriminação tátil e ela é controlada por essa placa, que vocês podem ver nessa imagem, que faz todo o sistema de controle do treinamento que é executado por um animal dentro dessa caixa. Dentro dessa caixa, desenvolvida por Krupa, o animal, ele entra dentro de um sistema de treino programado, onde o rato ele vai iniciar na câmera principal, que é essa maior aqui, ele vai iniciar o seu treino aqui dentro dessa seção, a porta, essa será aberta, ele vai ter acesso a essa zona que chama de câmara de discriminação. Nessa câmara de discriminação, ele vai se encontrar com esse nose poke central, onde ele vai ter que colocar o focinho aqui. As suas vibriças, que são os bigodes, elas estarão encostadas aqui nessas barras. Essas barras elas estarão em dois tipos de abertura. Ela estará com a abertura larga ou estreita. E o animal, quando ele entrar, colocar o focinho aqui nesse nose poke central, que ele sair e retornar para a câmara principal, ele vai ter que discriminar, dentro das suas vibriças por ter tocado aqui nas barras, se ele vai tomar a recompensa no lado esquerdo ou direito. Se for no esquerdo, a abertura foi estreita. Se for no direito, a abertura foi larga. Se ele errar, ele não recebe a recompensa. Alguns trabalhos publicados dentro do que estudaram o sistema somatosensorial desenvolvido por Krupa, vários trabalhos utilizaram esse modelo de caixa comportamental para fazer estudos bem específicos e bem positivos no ramo da ciência. Dentre eles também destaco o Brain-to-Brain Interface, que esse trabalho a gente fizemos a conexão de dois ratos, um no estado do Rio Grande do Norte e outro nos Estados Unidos, e ambos eles estavam conectados. O comportamento que ele executou em um canto na caixa, ele executou o outro ratinho, ele executou a mesma tarefa na outra, e eles ficaram conectados na sua zona de atividade. Outro trabalho, também publicado, que vem estudando a interação da conectividade, onde podemos ver como se manifesta a estrutura cerebral mediante a reação da tarefa de discriminação. A gente pode ver as bordas vermelhas, que indicam o aumento dessa conectividade, e as azuis indicam a diminuição dessa conectividade. Esses gráficos, eles mostram quais são as áreas sensoriais primárias, quantas áreas de ordem superior para direcionar respostas que estão relacionadas ao comportamento do animal. Sendo assim, queremos possibilitar, dentro desse modelo, experimentos complexos, como, por exemplo, pequenas variações de abertura e inserção de barras divisórias na câmara principal, facilitando e colocando outros tipos de treino nesse ambiente, portabilidade, baixo custo, utilização de elementos eletrônicos que temos no nosso mercado. Isso vai fazer com que a gente tenha uma caixa comportamental operante, Open Hardware, para estudo de discriminação tátil de pequenos roedores, de forma automatizada, autônoma, simples e com componentes nacionais. Sendo assim, o que nós vamos atingir de forma específica? Projetar um conjunto moderno e acessível, projetar suportes de câmera que possa fazer a gravação de todo o experimento, possibilitar o estudo de sistema sensório-motor de maneira mais refinada, uma vez que controlar com muita precisão a abertura das barras de discriminação é um elemento forte para esse tipo de treino, e fazer desenhos de experimentos mais complexos de tomada de decisão. Dentro disso, nossos materiais e etapa estrutural para se formalizar, ele veio de uma etapa computacional e uma etapa estrutural. A etapa computacional, ela vai desde motores e sensores, e a etapa estrutural vai toda a parte que compõe, desde o desenho e construção da caixa. Nos motores, eles estão localizados todos os tipos de motores utilizados na caixa. Eles foram motores servos motores, desde o modelo MG995, o SG90 e um motor de passo que a gente utilizou para fazer a utilização de mecanismos de controle e de que vai desde a abertura de portas, de barras e entrega de recompensas. Os sensores que a gente utilizou, eles se encontram nos nose pokers. Esses sensores é justamente para captar o momento que o animal ele toca o focinho no nose poker, desde para receber a recompensa ou para mostrar a localização no nose poker central. Ao tocar o focinho no nose poker, ele mostra que ele cortou o feixe e ele está na localização de uma etapa do treinamento. Na etapa computacional, utilizamos o Arduino para fazer toda a etapa de controle, ou seja, o Arduino ele vai substituir aquela placa imensa que foi mostrado nos primeiros slides, que faz todo o controle da caixa. Com o Arduino, nós podemos programar todos os tipos de treinos que for possível, carregar treinos diferentes e executar na caixa. O Arduino ele é possível fazer controle de diversos elementos inseridos em uma apenas placa de Arduino. A escolhida foi o Arduino Mega, devido ter uma maior diversidade, uma maior quantidade de portas para se utilizar e comportar de uma forma bem mais tranquila. O nosso treino, o nosso controle, ele vai se basear desde o momento em que a gente comanda o algoritmo através do computador para o Arduino. Do Arduino, a gente vai passar esse treinamento para a caixa. Essa etapa, ela vai fazer com que o nosso controle, o nosso experimento, ele funcione de forma autônoma. Sendo assim, ele vai ter algumas etapas. As etapas são: a primeira etapa, os módulos da câmara de discriminação eles serão ativados. Esses que estão em verde são todos os que estarão ativados no primeiro momento em que o animal é colocado dentro da caixa. Os que estão em vermelho, eles que estão inativos. No primeiro momento, o animal ele é colocado dentro da caixa, na seção principal, e ele vai começar o treinamento. Na segunda etapa, ele passa as segundas preliminares para o módulo de recompensa e acessibilidade das câmeras, e por último ele tem a liberação de recompensa, onde ele vai discriminar se está do lado esquerdo ou do lado direito, e assim acessando de uma forma correta ou errada. Caso ele erre, ele vai ter que começar todo o experimento novamente até ele acertar. A etapa estrutural, nós utilizamos o software SketchUp para fazer todo o desenho da caixa comportamental. Essa visão projetista de como seria a pessoa com relação à caixa. Então, a caixa ela tem todas essas etapas que vai desde a base até as câmeras. Todas as etapas foram desenhadas. A etapa da base. A base ela é composta por grelha, tampa da base, a base em si e a gaveta. Todo esse conjunto forma a base por inteiro, onde essa base será o alicerce, o ponto base, ponto fundamental para se colocar as paredes. Nas paredes, a gente tem um conjunto de 12 peças que são formuladas de acrílico, e todo esse conjunto ele é armado, certo? E parafusado de forma a deixar a caixa por inteiro. O Scott Walker é esse modelo que tem a responsabilidade de abrir e fechar, ou seja, empurrar de forma larga ou estreita a barrinha, onde o animal vai tocar com as vibriças. Esse Scott Walker, ele está localizado nessa parte frontal, na lateral. O Scott Walker, ele possui esse modelo, certo? Onde possui as barras indexadas a ele e o motor de passo, onde vai fazer esse controle de empurrar as barrinhas para um encontro da outra, deixando o espaço largo ou estreito para o animal discriminar. Os nose pokers é onde o animal temos um nose poker principal, onde ele toca e diz: poxa, eu entrei na câmara de discriminação. E aqui a câmara de recompensa, que é o segundo nose poker, onde ele recebe acoplado esse motor de passo que segura esse bloqueio aqui para o animal não receber a recompensa antes do tempo. Então, os nose pokers estão localizados nessa etapa. Esse aqui é o notebook principal, o seu desenho para indexar perfeitamente os sensores. A bomba de recompensa, que é esse conjunto onde o animal vai receber 50 microlitros de água como recompensa. Ele vai estar indexado a uma mangueira que vai ser colocada lá no notebook de recompensa e o animal vai receber esse conjunto exato de acordo com o que for programado. E, por fim, temos a cremalheira, que é esse conjunto, onde é composto para responsável para abrir e fechar a porta, que dá acesso de um compartimento a outro. Essa cremalheira, ela vai dar acesso à câmara principal, à câmara de discriminação. Ela vai fazer com que o animal ele não entre antes do tempo dentro do espaço discriminativo e o de recompensa. Ela vai ter essa função. E as câmaras de suportes, que estão aqui localizadas, que vai ter a função de justamente filmar todo o treino de uma forma em alta qualidade do que está sendo originado. E, por fim, nós temos a nossa caixa comportamental pronta, projetada, em todos os seus elementos incluídos, e ela fica dessa maneira com todos os seus elementos. A caixa, dessa visão que vocês podem estar observando, ela será utilizada nas mesmas dimensões que foi projetada a primeira. O animal ele consegue perfeitamente detectar alguma mudança, então algumas dimensões internas elas são fiéis à original para que não possa ter alteração no treinamento. Então, todas as visões, a visão interna da caixa, do acesso, como o animal se comportaria vendo, acessando cada elemento, como esse, a parte da discriminação, e, por fim, a visão das câmeras, mostrando o projétil aqui, a caixa por inteiro. Sendo assim, aqui a caixa construída de acrílico, muitos materiais, a caixa toda foi utilizada de acrílico, construída de acrílico e material de impressão 3D em ABS. Então, a caixa principal, paredes, bases, toda em acrílico e as outras peças são utilizadas ABS e impressão 3D. Por fim, esse trabalho vai propor que outros laboratórios possam ter ferramentas mais acessíveis para desenvolvimento desse projeto na área de discriminação tátil, e todos esses passos de desenvolvimento eles vão ser utilizados em uma plataforma colaborativa multiusuária, onde vamos ter um manual de desenvolvimento do projeto, o procedimento de automatização do sistema de servomecanismo e a montagem do aparelho. Queremos, por fim, colaborar dessa forma, as nossas referências principais, algumas que nós utilizamos. Muito obrigado.
Ok, obrigado, José. Anderson, parabéns pelo trabalho. E gostaria de saber se tem alguma pergunta.
Eu tenho uma, né?
Diga.
Legal, Luiz. José, legal, eu gosto de trabalhos aplicados, assim, os professores nossos dizem, esse é um exemplo de trabalho de engenharia, onde a gente projeta e constrói. E, assim, eu tenho uma pergunta, assim, eu não sei se você chegou a pesquisar isso, mas você enfatizou que a ideia do seu trabalho era desenvolver uma câmara que fosse controlada, mas especialmente que ela fosse open hardware, open software, né, e com materiais encontrados no mercado nacional. Quais são as opções que existem hoje? Porque, com certeza, esses experimentos já são feitos por aí na engenharia biomédica ou nos outros tipos de pesquisa que usam camundongos, né? Então, quais são as opções que existem? Você já chegou a comparar com a sua versão em termos de custo e de possibilidades?
Assim, de materiais, o modelo anterior, que foi construído por grupo, ele está parado, certo? Ele está parado devido a ter peças que a gente não encontra aqui. Um exemplo, tem o sistema de barras que ele utiliza, é um sistema bastante robusto que a gente não consegue recompor. Então, assim, com esse modelo que a gente construiu, desde o servo, o sistema de Scott-Yoke, que é uma solução que a gente não tem atrito no abrir e fechar das barras, não emite barulho que interrompe o animal, ele detecta essas vibrações, esses barulhos, interrompe no treinamento. Uma outra coisa, a forma das barras, das portas deslizantes, que eu coloquei rolamentos, que justamente faz com que ela tenha uma resposta rápida na abertura do compartimento. E os treinamentos que são feitos, certo? O Teses, por exemplo, eles utilizam bem menos recursos, bem menos materiais que essa caixa. Então, assim, para a construção dela, eu acho que é essa sua linha, né, essa pergunta, com relação ao material.
Sim, eu queria mais saber as opções que já existem, né? O que o pessoal já usa, que a tua possibilidade, que a sua caixa especificamente, ela resolve esse problema.
Isso. Assim, é uma caixa que ela vai atuar muito nessa parte de recompor os treinos que estão parados nessa parte de discriminação. Porque existem vários tipos de caixas. Então, assim, para cada caixa eu posso ter uma determinada aplicação. E ela vai possibilitar, por exemplo, treinamento forçado. A de Krupa não faz, essa daqui faz. Soluções de mais de 20 anos não tinham de fazer uma única caixa, diversos treinamentos, com essa a gente consegue. As que estão aí não conseguem. Eu consigo fazer inserção de uma barra, de 2 barras dentro da caixa, sem interromper o treinamento. Posso fazer treinamento forçado, unilateral, bilateral. Ou seja, ela me traz múltiplas opções de uso. E além de que, quando você falou da parte de open hardware, essa questão deixar ela autônoma é porque a antiga tinha muita interrupção do usuário. Tem que ter uma pessoa assistindo o treino. Com esse modelo, não preciso. Ele já faz tudo automático. Entendeu? Ela está programada para isso.
Entendi, obrigado.
Alguma outra pergunta? Do YouTube?
Tem uma aqui. Obrigado.
Tá. Eu tenho uma pergunta. José Anderson, você falou que vai acoplar câmeras, né, na tua caixa. Você tem previsto algum tipo de hardware embarcado para processar as imagens capturadas por essa câmera? Além de hardware, software também para capturar, para pegar essas imagens e retirar alguma informação útil?
A princípio, o que eu pretendo é utilizar o mesmo sistema de captação do anterior. Eu ainda não decidi um novo para fazer uma captação paralela para fazer esse registro. Até então, eu estou dentro dessas duas possibilidades.
Quando você fala de anterior, seria uma versão anterior que você já construiu?
A versão anterior, eu não construí. É a mesma que a gente utilizou anteriormente, porque essa caixa vai ter que ser utilizada, os testes, né? A gente vai ter que fazer testes nela no instituto que eu desenvolvi anteriormente, que eu comecei a utilizar o projeto. Então, a gente vai precisar de 8 a 12 ratos para fazer essa validação, e esse sistema integrado de câmeras, a gente tem como fazer lá.
Ok, está previsto então no teu projeto, né?
Isso.
Ok, obrigado. Alguma outra pergunta? Não, nenhuma pergunta. Bom, gente, então finalizamos as apresentações do workshop de tese e dissertações. Amanhã, às 15h30, a gente tem a primeira sessão do concurso de teses e dissertações em robótica, certo? A primeira sessão são de trabalhos de mestrados que serão apresentados, e depois da sessão de mestrado, a gente tem às 16h50 a sessão de doutorado, certo? Onde trabalhos de doutorado serão apresentados. E esses trabalhos serão julgados. Inclusive, tem um juiz aqui na nossa sala, né, o professor Eduardo Totti, e quero agradecer publicamente a disposição do professor Eduardo em fazer parte do corpo de jurados que analisará os trabalhos amanhã do concurso de teses e dissertações. E quero também agradecer a todos que estão nos assistindo, nos prestigiando no workshop de teses e dissertações. Ok? Boa tarde a todos e nos vemos amanhã.
Obrigado, pessoal. Obrigado pela presença. Finalizando o dia de hoje do LARS. Obrigado a todos presentes. Obrigado por sua área, né?
Valeu,
e espero nos encontrarmos amanhã.